Hello and welcome to Space Historians. Tonight, we journey far from Earth, beyond Mars, beyond the asteroid belt, into the realm of the giant planets where Jupiter reigns supreme. And there, caught in the crushing grip of the largest world in our solar system, orbits a moon that refuses to be quiet. This is not a world of gentle landscapes or ancient craters preserved in stillness. This is not a frozen sphere, drifting peacefully through space. This is Io, and it is burning. Right now, at this very moment, dozens of volcanoes are erupting across its surface. Fountains of molten rock shoot hundreds of kilometers into space. Lakes of lava the size of cities overturn their crusts in cycles of heat and darkness. Mountains taller than Everest crack and crumble under stresses no earthly range has ever endured. The entire moon flexes and bends under Jupiter's gravitational pull, squeezed and released like a ball of putty in an invisible hand. Io is the most volcanically active body in the putty solar system. Not just more active than Earth, more active than all of Earth's volcanoes combined. More active than anything we have ever discovered anywhere, and it does all of this in complete silence. There is no roar of eruptions, no rumble of earthquakes, no rush of wind. The atmosphere is so thin it might as well not exist. Every explosion, every flow of lava, every fountain reaching toward the stars unfolds in the perfect quiet of space. It is violence without sound, fire without noise, a world burning eternally in stillness. Before we begin this journey together, I want to ask you something. Have you ever felt trapped between opposing forces, pulled in different directions by circumstances beyond your control? That is Io's existence, forever caught between Jupiter's immense gravity and the gravitational tugs of its sibling moons. It cannot escape, it cannot rest, it can only burn. And somehow, in that endless burning, there is a strange beauty, a world painted in colours no other moon can match: yellows, oranges, reds, whites, and blacks splashed across its surface like an artist's palette. A world where change is the only constant, where nothing remains the same from one orbit to the next. If you find peace in these explorations of the cosmos, if you enjoy drifting through space and time at a gentler pace, I would be grateful if you would consider liking this video or subscribing. It helps others find their way here, and together we can make these late hours feel a little calmer, a little more connected to the vast universe beyond our small world. Now, settle back, let your breathing slow. Imagine yourself lifting away from Earth, rising through the atmosphere, past the moon, past Mars, accelerating through the darkness until Jupiter's massive form appears before you. And there, a small golden-orange bead catches the sunlight. That is Io. From this distance, it looks peaceful. A small moon, barely larger than our own, circling the striped giant. But as we draw closer, the truth reveals itself. This is no quiet companion. This is a world at war with itself, shaped by forces beyond its control, burning with energy that has no outlet except violence. Tonight, we will drift slowly through Io's story. We will witness the discovery that shattered expectations. We will understand the science that explains its fury. We will see landscapes that exist nowhere else. And we will find, perhaps surprisingly, that even in violence there can be wonder. Even in restlessness there can be a kind of rhythm. Even in fire there can be peace. The universe is vast and full of mysteries, but few are as dramatic, as extreme, or as hauntingly beautiful as Io. A moon that cannot rest. A world that burns forever. The most violent body in our solar system. Let us begin. There are worlds in our solar system that sleep, Our moon is one of them. Its surface barely changed in billions of years, cratered and quiet, a memorial to impacts long past. Mars sleeps too, its giant volcanoes dormant for millions of years, its surface carved by ancient rivers that no longer flow. Even many of Jupiter's other moons rest in frozen stillness, their surfaces records of the deep past, preserved in ice and rock. But Io does not sleep. It cannot. It will not. Io is a moon in perpetual torment, caught in a gravitational dance it can never escape, forced to flex and bend and heat from within until its very rock melts and bursts forth. It is a world where rest is impossible, where calm is a foreign concept, where the only constant is change and the only certainty is violence. To call Io the most violent moon in our solar system is not hyperbole. It is simple fact, measured and verified by decades of observation. More than 400 active volcanoes dot its surface. At any given moment, dozens are erupting. The heat it releases exceeds that of all Earth's volcanic activity combined by a factor of 100 or more. Lava fountains arc hundreds of kilometers into the vacuum of space. The surface is repainted constantly, buried under fresh flows, coated with sulfur frost, reshaped so quickly that maps become obsolete within months. To understand the scale of this violence, imagine standing on Earth during the most catastrophic volcanic eruptions in human history. Mount Vesuvius burying Pompeii, Krakatoa exploding with such force the sound circled the globe, Mount St. Helens ripping itself apart. These were among the most powerful geological events humans have ever witnessed, and they were rare once in a lifetime, once in centuries. On Io, such violence is ordinary. It is Tuesday. It is every day and every hour. The eruptions never stop, never pause, never allow the surface a moment of stillness. The fountains that rise from Io's volcanoes reach heights that dwarf anything on Earth. The plume from a volcano called Pele extends more than 300 kilometers into space, higher than the International Space Station orbits above Earth. If you could stand on Io's surface and watch, you would see these fountains arcing silently overhead, spreading outward like great umbrellas, before falling back to coat the ground in layers of sulfur and ash. The lava lakes scattered across Io's surface are equally extreme. Loki Patera, the largest, spans more than 200 kilometers across an area that could swallow several small countries. Its surface churns and overturns in cycles lasting months, brightening as fresh molten rock wells up from below, darkening as it cools. The heat released from this single lake exceeds the output of all of Earth's volcanoes. One feature on one moon, outshining our entire planet's volcanic activity. This is not a world that evolved into violence slowly. Io has been this way for as long as we have observed it, and likely for billions of years before. The violence is not temporary, not cyclical, not waiting to quiet down. It is permanent, sustained by forces that will continue as long as Jupiter's gravity holds Io in its grip, and as long as its sibling moons, Europa and Ganymede, continue their orbital dance that keeps Io's path elliptical rather than circular. The elliptical orbit is key. As Io moves closer to Jupiter, the giant planet's gravity pulls harder on the side facing it than on the far side. As Io swings farther away, the pull lessens. This constant squeezing and releasing flexes the entire moon, bending it, stretching it, generating friction in its interior. That friction creates heat, enormous amounts of heat, heat enough to melt rock into magma, heat enough to drive eruptions that never cease. The moon is literally being kneaded like dough, over and over, orbit after orbit, forever. To picture this, Imagine holding a rubber ball and squeezing it rhythmically, again and again, without stopping. Eventually, your hands would tire, but the ball would heat up from the constant compression. Now imagine that process scaled up to an entire world, squeezed not by hands, but by the gravity of the largest planet in the solar system, compressed not for minutes, but for billions of years. That is Io's existence, and the result is a surface unlike any other. Where most moons are grey or white or tan, Io blazes with colour. Yellows, oranges, reds, blacks, whites, all painted across its face in patterns that shift and change. Sulfur compounds, heated and altered by volcanic activity, create this alien palette. From space, Io looks like a pizza, a description scientists half-jokingly applied when Voyager first sent back images in 1979. But the comparison, while amusing, undersells the strangeness of the reality. This is not just a colourful moon, it is a world where the ground can rise and fall by more than 100 metres during each orbit as tidal forces lift and compress the crust. It is a world where nothing, no crater, no mountain, no plain survives unchanged for long. Everything is temporary. Everything is waiting to be buried or melted or fractured. The mountains of Io are another expression of this restlessness. Some tower more than 17 kilometers high, nearly twice the height of Everest. But they are not formed by tectonic collision like Earth's ranges. They are blocks of crust thrust upward by internal stresses, tilted and fractured, unstable from the moment they form. Their slopes are marked by landslides, their peaks jagged and raw. They rise, they endure for a time, and then they collapse or are buried by flows. Nothing lasts. Even Io's thin atmosphere participates in the cycle of violence. What little gas exists, primarily sulfur dioxide released by eruptions, collapses at night when temperatures plunge and reforms during the day when sunlight warms the frost. The atmosphere vanishes and reappears with each rotation, another manifestation of the moon's inability to find balance. All of this violence, all of this heat, all of this constant reshaping occurs in absolute silence. Io's atmosphere is far too thin to carry sound. There is no air to transmit the roar of eruptions, no medium to carry the crack of fracturing mountains or the hiss of escaping gas. The violence is purely visual fire and motion unfolding in perfect quiet. That silence makes it both more alien and, strangely, more peaceful to contemplate. The eruptions do not assault the senses with noise. They simply are, glowing and arcing and falling in a ballet of destruction that never makes a sound. For scientists, Io is invaluable. It is a natural laboratory showing processes that occurred on Earth billions of years ago, when our planet was younger and hotter. It demonstrates tidal heating on a scale impossible to reproduce artificially. It proves that small worlds can be just as geologically active as large ones if the right conditions exist. And it challenges assumptions about where and how volcanism can occur. For the rest of us, Io is a reminder of extremes. It shows that the universe contains worlds more violent than we might imagine, but also that violence and beauty are not opposites. Io's painted surface, its glowing lava lakes, its soaring plumes, these are beautiful in their own alien way, even as they represent forces that would instantly destroy anything human that ventured too close. To think of Io is to think of energy that will not be contained, of restlessness that has no cure, of a world that exists in a state of permanent upheaval. It is a world that cannot rest because the forces that shape it, gravity, orbit, resonance, will not allow rest. It is trapped in its violence as surely as it is trapped in its orbit, and yet there is something almost soothing about its predictability. Io will continue erupting tomorrow and next year, and 1,000 years from now. Its violence is not random chaos, but the steady expression of physical laws. It is reliable in its restlessness, constant in its change. There is a rhythm to it, a pattern, even if that pattern is one of perpetual destruction and renewal. As we begin this journey through Io's story, we carry with us this fundamental image: a small moon, burning silently in space, unable to rest, unable to cool, forever caught between the gravitational giants that shape its fate. A world that teaches us about the limits of violence, about the beauty that can exist within extremes, about what it means for a place to be truly, utterly incapable of peace. Io cannot rest. And tonight we will understand why. To understand Io, we must first understand where it resides, the neighborhood it inhabits, and the cosmic architecture that determines its fate. Io does not drift alone through space. It is part of a system, a family of worlds bound to Jupiter, the largest planet in our solar system, a gas giant so massive that it contains more than twice the mass of all the other planets combined. Jupiter orbits the Sun at a distance of about 778 million kilometers, far beyond the warmth that makes Earth habitable, out where sunlight is weak and space is cold. Yet even at that distance, Jupiter dominates its region of the solar system. Its gravity shapes the orbits of countless objects, asteroids, comets, and especially its many moons. Jupiter has at least 95 known moons, though that number continues to grow as smaller satellites are discovered. But among all these companions, 4 stand out, visible even through a modest telescope. These are the Galilean moons, named for Galileo Galilei, who first observed them in 1610. They are Io, Europa, Ganymede, and Callisto, each distinct in character, each shaped by different forces, each a world in its own right. Io is the innermost of the 4, orbiting Jupiter at a distance of approximately 422,000 kilometers, only slightly farther than the Moon orbits Earth. This proximity places Io deep within Jupiter's gravitational well, close enough that the planet looms enormous in its sky, filling nearly 20 degrees of arc, more than 40 times wider than the Moon appears from Earth. If you could stand on Io's surface and look up, Jupiter would dominate your view, a vast striped sphere hanging perpetually in the sky, its bands of clouds swirling slowly, its great red spot occasionally visible, a storm larger than Earth itself. The planet would never rise or set because Io is tidally locked, always showing the same face to Jupiter, just as our Moon always shows the same face to Earth. Jupiter would simply hang there, massive and unchanging in position, though its cloud patterns would shift with time. Beyond Io lies Europa, orbiting at about 671,000 kilometers from Jupiter. Europa is a world of ice, its surface a frozen shell covering what scientists believe is a vast ocean of liquid water. Where Io is volcanic, Europa is icy. Where Io is painted in sulfur colors, Europa gleams bright white, its surface crisscrossed with cracks and ridges, but notably lacking in craters, suggesting that it too is young, its ice constantly resurfacing, through processes we are only beginning to understand. Farther out orbits Ganymede, the largest moon in the solar system, bigger even than the planet Mercury. Ganymede circles Jupiter at about 1.07 million kilometers, far enough to escape the most intense gravitational stresses, but still bound to the system. Its surface is a mix of ancient dark terrain and younger grooved regions, evidence of past geological activity, though nothing approaching Io's current violence. Finally, farthest of the 4, comes Callisto, orbiting at 1.88 million kilometers. Callisto is ancient, its surface saturated with craters accumulated over billions of years. It is the quiet one, the spectator, largely unchanged since the solar system's youth. Its heavily cratered face stands in stark contrast to Io's crater-free violence, a reminder of what Io might look like if it were not constantly erasing its own history. These 4 moons form a miniature solar system within the larger solar system. They orbit Jupiter in the same plane, their paths determined by the same gravitational laws that govern planets around the Sunday. But they are not independent. They influence each other through subtle gravitational tugs, and in the case of Io, Europa, and Ganymede, they are locked in a precise orbital resonance that has profound consequences. The resonance works like this. For every time Ganymede completes 1 orbit around Jupiter, Europa completes exactly 2 orbits, and Io completes exactly 4. The ratios are perfect. 4, 2, 1. This is not coincidence, but the result of gravitational interactions over billions of years that have locked the 3 moons into synchronized motion. Every time the moons align in certain configurations, they tug on each other gravitationally. These tugs are small compared to Jupiter's overwhelming pull, but they are persistent, and they have a critical effect. They prevent Io's orbit from becoming circular. Without Europa and Ganymede's influence, Io's orbit would gradually circularize through tidal interactions with Jupiter. The orbit would become a perfect circle. Io would always be at the same distance from Jupiter, and the tidal forces would become constant. The squeezing and releasing that generates Io's internal heat would stop, and the moon would cool, its volcanoes falling silent. But the resonance prevents this. Europa and Ganymede's regular gravitational nudges maintain a slight eccentricity in Io's orbit. That eccentricity is small, only about 0.004, but it is enough. Enough to ensure that Io alternates between being closer to Jupiter and farther away. Enough to maintain the tidal pumping that generates heat. Enough to guarantee that Io will never find peace. The setting of Io's story is therefore not just a location in space, but a gravitational trap. It is caught between Jupiter's crushing gravity and the persistent nudges of its siblings, unable to circularize its orbit, unable to stop flexing, unable to cool. The architecture of the system, the distances, the masses, the resonance, all conspire to keep Io in a state of perpetual geological violence. This setting also places Io within Jupiter's magnetosphere, one of the most intense radiation environments in the solar system. Jupiter's magnetic field is enormous, extending millions of kilometers into space, and it is powerful, far stronger than Earth's. Charged particles trapped in this field create radiation belts that would be lethal to unprotected humans. Io orbits directly through these radiation belts, but rather than being simply a victim of Jupiter's magnetosphere, Io actively shapes it. The volcanic eruptions constantly eject material into space: sulfur, sulfur dioxide, sodium, and other compounds. Much of this material escapes Io's weak gravity and becomes ionized by Jupiter's radiation, forming a vast torus of plasma that encircles Jupiter along Io's orbital path. This plasma torus glows faintly in ultraviolet light, invisible to human eyes but detectable by spacecraft instruments. It is a giant ring of charged particles, fed continuously by Io's eruptions, swept along by Jupiter's rotating magnetic field. In this way, Io's influence extends far beyond its small body, reaching out to shape the space environment of the entire inner Jovian system. The interaction between Io and Jupiter's magnetosphere also creates electrical currents that flow along magnetic field lines connecting the moon to the planet. These currents, carrying millions of amperes, help generate auroras at Jupiter's poles, vast ovals of light far more powerful than Earth's northern and southern lights. Io's volcanic eruptions thus don't just shape the moon's surface, they paint lights in Jupiter's atmosphere. The setting of Io is therefore dynamic, interconnected, and violent. It is not a moon orbiting in isolation, but a participant in a complex system of gravitational resonances, magnetic interactions, and plasma physics. Every aspect of its environment contributes to making it what it is, a world in torment, unable to rest. From Earth, we cannot perceive any of this complexity. Through a telescope, Jupiter appears as a bright, banded disk. And if the telescope is good enough, the 4 Galilean moons appear as tiny points of light, shifting position from night to night. Io looks peaceful from that distance, just another satellite dutifully circling its planet. But zoom in, send spacecraft to visit, measure, and observe with instruments more sensitive than human eyes, and the truth emerges. That peaceful-looking dot is burning. That small moon is the most geologically active body in the solar system. That seemingly insignificant satellite is powerful enough to shape phenomena on a planet 1,000 times more massive than itself. The setting is the key to understanding Io. Without Jupiter's immense gravity, there would be no tidal heating. Without Europa and Ganymede's resonance, the orbit would circularize and the heating would stop. Without the magnetosphere, Io's ejected material would simply drift into space rather than forming a torus and generating auroras. Every element of the system contributes to Io's character. As we prepare to trace Io's story from its discovery to modern understanding, we carry with us this image of its setting, a small moon in the inner court of a giant planet, trapped in an orbital resonance with its siblings, bathed in intense radiation, flexing constantly under gravitational stress, ejecting material into space that feeds a glowing torus and creates auroras on Jupiter. It is a setting of extremes, of interconnected forces, of consequences that ripple outward from a moon barely larger than our own. It is the perfect stage for the most violent geological show in the solar system, a setting that ensures Io can never rest, never cool, never find the peace that other moons enjoy. And it all happens in the cold darkness, 778 million kilometers from the Sun, where Jupiter's family of worlds dances on, locked in their ancient rhythms, indifferent to our observations, but endlessly fascinating to our curiosity. There is something profound about the moment when a point of light becomes a world, when what seemed like a simple star reveals itself to be something far more complex, something that challenges our understanding of the cosmos. For Io, that transformation began on a winter night in January 1610, though the full revelation would take more than 3.5 centuries to unfold. Galileo Galilei had heard of a new invention from the Netherlands, a spyglass that made distant objects appear closer. He immediately understood its potential not for naval warfare or surveying land, but for looking upward. By late 1609, Galileo had built his own version, improving the design until he had a telescope capable of magnifying objects about 20 times. It was crude by modern standards, with imperfect lenses and a narrow field of view, but it was enough to change everything. On the 7th of January 1610, Galileo turned his telescope toward Jupiter, the brightest object in the evening sky after the Moon and Venus. Jupiter appeared as a small disk, far clearer than the naked eye could discern, showing hints of its banded atmosphere. But what caught Galileo's attention that night were 3 small stars arranged in a straight line near Jupiter, 2 on one side and 1 on the other. The next night, he looked again. The stars had moved. All 3 were now on the same side of Jupiter. This was strange. Stars were supposed to be fixed in their constellations, and Jupiter moved slowly across them over months, not nights. Yet, these stars had clearly changed position relative to the planet. Galileo continued observing night after night, sketching what he saw. On January 13, he observed 4 of these stars rather than 3. By January 15, he had realized the truth. These were not stars at all. They were moons, satellites orbiting Jupiter, just as our moon orbits Earth. They moved because they were bound to the planet, circling it in periods ranging from less than 2 days to about 17 days. He named them the Medicean stars in honor of his patron, Cosimo II de' Medici, though that name did not endure. Later astronomers called them the Galilean moons, and eventually they received individual names drawn from Greek mythology: Io, Europa, Ganymede, and Callisto, all figures associated with Zeus, Jupiter's Greek counterpart. For Galileo, this discovery was revolutionary. It proved decisively that not everything in the heavens orbited Earth. Here was a miniature system, a planetary model in miniature, with moons circling Jupiter. If moons could orbit Jupiter, then perhaps planets could orbit the Sun, supporting the Copernican model that placed the Sun at the center rather than Earth. The discovery was dangerous. The prevailing geocentric model, endorsed by the Church, placed Earth at the center of creation. To suggest otherwise was to challenge theological doctrine. Galileo published his findings anyway, in a book called Sidereus Nuncius, the Starry Messenger, in March 1610. The book described his observations and their implications, marking one of the pivotal moments in the scientific revolution. But for Io itself, the discovery was just the beginning of a very long mystery. In Galileo's telescope, and in all telescopes for the next 3.5 centuries, Io appeared as nothing more than a point of light. It moved predictably, completing its orbit around Jupiter in 1.769 days. It was the innermost of the 4 moons, the fastest, but otherwise it revealed nothing of its nature. As telescopes improved through the 17th, 18th, and 19th centuries, astronomers learned more about Io's orbit. They measured its period with great precision. They calculated its distance from Jupiter and estimated its size. By the early 20th century, they knew Io was about 3,643 kilometers in diameter, slightly larger than our moon, making it the 4th largest moon in the solar system after Ganymede, Titan, and Callisto. Some observers noted that Io appeared to have a faint orange or yellowish tint, different from the whiter appearance of Europa or the darker tones of Callisto. But this colour was subtle and difficult to interpret. Did it indicate surface composition, atmospheric effects? No one knew. The regularity of Io's orbit made it useful for a surprising purpose: navigation. In the 17th century, determining longitude at sea was one of the great challenges facing sailors. Latitude could be measured by observing the sun or stars, but longitude required knowing the time at a reference point, and accurate clocks did not exist yet. Giovanni Domenico Cassini and others realized that Io's eclipses, when it passed into Jupiter's shadow, occurred at predictable times and could be observed from anywhere on Earth, weather permitting. By comparing the local time when an eclipse was observed to the time it was predicted to occur, at a reference meridian, navigators could calculate their longitude. Io, that small dot of light, became a cosmic clock, helping ships cross oceans and map the world. But what was Io itself like? The question remained unanswered for centuries. Speculation abounded. Some thought it might be icy, like Europa. Others imagined it covered in rock and dust, like our moon. The orange tint suggested something unusual, but without the ability to resolve surface features, there was no way to know. Even as late as the 1,970 seconds, After decades of modern astronomy and the beginning of the space age, Io remained mysterious. Scientists had learned more about its mass and density, determining it was more rock than ice. Unlike the outer Galilean moons, spectroscopic observations suggested the presence of sulfur compounds on its surface, explaining the colour, but the details were still hidden. The best pre-spacecraft observations came from ground-based infrared telescopes in the 1,970 seconds, which detected unusual heat emissions from Io. Some regions appeared warmer than they should be based on sunlight alone. This was puzzling. What could be heating Io's surface? At the same time, theoretical work was advancing. In 1979, just before the Voyager 1 spacecraft reached Jupiter, a scientist named Stanton Peele published a paper with colleagues predicting that Io might be volcanically active due to tidal heating. The resonance with Europa and Ganymede, combined with Jupiter's strong gravity, should generate enough internal friction to melt rock. The paper concluded that Io should have active volcanoes. This prediction was bold and controversial. Volcanism was known on Earth, and evidence existed for ancient volcanism on Mars and Venus. But active volcanism on a small moon seemed unlikely. Moons were supposed to be geologically dead, their small sizes allowing them to cool quickly after formation. Yet the mathematics of tidal heating were compelling. The energy budget worked out. If the theory was correct, Io should be erupting. But no one had ever observed such activity, and many remained skeptical. Then Voyager 1 arrived. The spacecraft, launched in 1977, reached Jupiter in March 1979 after an 18-month journey. Its cameras were designed to capture images of Jupiter and its moons with unprecedented clarity. As it approached Io, scientists prepared for what they expected: a rocky, cratered surface similar to our Moon or Mercury. What they saw instead shocked everyone. Io's surface was smooth, almost devoid of craters. It was painted in vivid yellows, oranges, and reds, unlike any world yet seen. And on the 9th of March, 1979, a navigation engineer named Linda Morabito was examining an image taken to check Voyager's pointing accuracy when she noticed something extraordinary in the background. There, rising from Io's limb, was a vast plume of material extending hundreds of kilometers into space. An eruption, a volcanic plume, active volcanism on another world, caught in the act. The discovery made headlines worldwide. Scientists scrambled to examine other images, finding evidence of multiple plumes, of lava flows, of recent volcanic activity across the surface. Io was not dead. It was the most volcanically active body in the solar system. The 369-year journey from a point of light in Galileo's telescope to a world of fire was complete. Io had been transformed from a wandering star to a moon, from a moon to a mysterious coloured disk. Each generation of observers had added a piece to the puzzle, but it took Voyager's close flyby to reveal the full picture. Galileo's discovery in 1610 had proven that not everything orbits Earth. Voyager's discovery in 1979 proved that not all moons are dead. Between those two moments stretched centuries of patient observation, each generation building on the last, each adding to our understanding of this small, strange world caught in Jupiter's grip. The discovery of Io was not a single moment, but a long unfolding, a gradual revelation that reminds us how slowly the universe gives up its secrets. What began as a wandering star became one of the most fascinating worlds in the solar system, a place where every assumption about moons had to be reconsidered, where the impossible constant volcanism on a body smaller than Earth's moon turned out to be undeniably real. There are moments in science when expectations shatter so completely that the only response is stunned silence followed by frantic activity. The first clear images of Io from Voyager 1-inch March 1979 created exactly such a moment. Scientists had gathered at the Jet Propulsion Laboratory in Pasadena, California, to watch as images arrived, transmitted across nearly 650 million kilometers of space, taking almost an hour to travel from spacecraft to Earth at the speed of light. They expected a rocky, cratered moon. They got a pizza. That was the immediate, half-serious comparison that sprang to mind when the first high-resolution color images appeared on screens. Io looked like nothing anyone had ever seen, a sphere mottled with yellows, oranges, reds, blacks, and whites, with patterns that seemed almost organic, almost painted. One scientist joked it looked like a pizza topped with melted cheese and pepperoni. The comparison stuck, appearing in newspapers and broadcasts around the world. But beneath the humor was genuine astonishment. This was wrong. This was not what moons were supposed to look like. The most immediate shock was the absence of craters. Every other rocky body yet examined, Mercury, the Moon, Mars, even the asteroids, was covered in impact craters, the accumulated scars of billions of years of bombardment. Craters were the default surface feature, the expected signature of age and geological inactivity. Io had almost none. A few small pits could be seen in some images, but the large, obvious craters that dominated other worlds were simply absent. This could mean only one thing. Io's surface was young, constantly renewed by some process that buried or erased craters faster than they could accumulate. The colors added to the strangeness. Bright yellows and oranges dominated large regions, interspersed with dark patches and brilliant white spots. The patterns were irregular, chaotic, unlike the ordered features of planets shaped by tectonic processes. Some regions showed circular patterns, bright rings surrounding darker centers. Others showed what appeared to be flows, dark streaks extending across the colorful plains. The science team worked through the night, analyzing image after image as Voyager sped past. The spacecraft's closest approach to Io came on March 5, passing within 20,600 kilometers of the surface. At that distance, features as small as a few kilometers across could be resolved, and what those features revealed was increasingly bizarre. Mountains rose to staggering heights, some more than 10 kilometers tall, taller than anything on Earth. But they were not volcanic cones as expected. They were massive blocks, tilted and fractured, standing alone rather than in chains. Cliffs dropped sheer for kilometers. The terrain was violent, stressed, broken. Dark patches on the surface appeared to be lava flows, some with clear flow fronts where molten material had advanced and cooled, but the bright yellows and reds remained mysterious. Spectroscopic analysis suggested sulfur compounds, which could exist in different colors depending on temperature and form. But why so much sulfur? And why such vivid colors? Then came the plumes. Linda Morabito, a navigation engineer, was examining an image taken for spacecraft navigation purposes. The image showed Io's crescent, lit from behind by sunlight. Morabito was checking the position of background stars when she noticed something odd. A large, umbrella-shaped cloud extending from Io's limb, rising far above the surface. At first, she thought it might be another moon visible, behind Io. But the geometry was wrong. The feature was attached to Io itself. It was an eruption plume, a fountain of gas and particles shooting more than 300 kilometers into space. The discovery electrified the science team. They went back through other images, looking for similar features. They found 8 more active plumes in the Voyager 1 images. 9 volcanic eruptions caught in the act, visible because they rose high enough above the surface to be silhouetted against space. Each plume had a characteristic shape, a bright column rising from the surface, spreading outward at the top like an umbrella or fountain, then falling back in graceful arcs. The particles followed ballistic trajectories in Io's weak gravity, creating symmetrical patterns, and the scale was enormous plumes reaching hundreds of kilometers high, some spreading deposits across thousands of square kilometers of surface. The implications were staggering. This was not occasional volcanism, not rare eruptions, separated by centuries of quiet. This was constant, ongoing activity on a scale that dwarfed Earth. 9 active eruptions visible in a single flyby suggested dozens or hundreds might be active at any given time across the surface. Stanton Peele and his colleagues, who had predicted tidal heating and volcanism just weeks before Voyager's arrival, were vindicated in the most spectacular way possible. Their paper, which had seemed speculative, turned out to be precisely correct. Io was heated by tidal forces. It was volcanically active, and it was far more active than even they had dared predict. The press conference held at JPL to present the results was remarkable. Scientists showed image after image of a world that defied easy description. They explained tidal heating, orbital resonance, sulfur volcanism. They described a moon caught in a gravitational vice, constantly flexing, generating heat that had nowhere to go but outward in volcanic eruptions. The public response was enormous. Io appeared on magazine covers. The Pizza Moon moniker spread. But more importantly, a fundamental shift occurred in how people thought about the solar system. Moons were not just dead rocks. They could be geologically active. They could be strange and colourful and violent. The solar system was more diverse, more dynamic, more interesting than previously imagined. For planetary scientists, Io became an obsession. Papers analysing the Voyager data poured out over the following months and years. Every aspect was studied. The composition of the plumes, the temperature of the lava flows, the structure of the mountains, the chemistry of the colourful deposits, the interaction with Jupiter's magnetosphere. The discovery of Io's volcanism also raised new questions. How deep was the heating? Was there a global magma ocean beneath the crust? How long had this activity been going on? Were the plumes water vapour or something else? Spectroscopy soon confirmed they were primarily sulfur dioxide. How did the constant resurfacing work? How fast were features being buried? Voyager 2 followed 4 months later, passing Io at greater distance but still capturing valuable data. Importantly, some of the plumes seen by Voyager 1 had disappeared, while others persisted and new ones had appeared. This confirmed that the volcanism was not only active but variable, changing on timescales of months. The 2 Voyager flybys had transformed Io from a mysterious coloured dot into the most volcanically active world known. They had revealed a surface younger than any other, painted in colours found nowhere else, shaped by processes more extreme than anything on Earth. They had shown plumes rising into space, lava flows spreading across plains, mountains fractured by unimaginable stresses. The initial response, stunned amazement followed by intense scientific analysis, established Io as one of the most important targets in planetary science. It was not just interesting because it was strange. It was important because it demonstrated fundamental processes: tidal heating as a power source, the role of orbital resonance, the effects of constant resurfacing, the connection between a moon and its planet's magnetosphere. The pizza comparison, amusing as it was, undersold the significance. Io was not a joke or a curiosity. It was a revelation, a world that forced scientists to expand their understanding of what was possible. It showed that small bodies could be more active than large ones, if the right conditions existed. It proved that moons could shape planetary environments. It demonstrated that the solar system held surprises, waiting for those who looked closely enough. As the images circulated and the data was analyzed, the first response evolved from surprise to understanding. Io made sense once you understood the forces acting on it. Its strangeness had explanations rooted in physics. Its violence was not random, but inevitable, given its orbital situation. And, perhaps most remarkably, Io had been this way all along. For 369 years after Galileo's discovery, humans had looked at this point of light without realizing it was a world on fire. The eruptions visible in Voyager's images had been occurring all that time, unseen, unknown, waiting for technology to advance enough to reveal them. The first response to seeing Io clearly was astonishment. The lasting response would be fascination, study, and a determination to understand not just what Io was, but why it existed and what it could teach us about worlds both near and far. There is something deeply unsettling about violence in silence. We are accustomed to noise accompanying force, the crack of thunder, the roar of wind, the rumble of earthquakes. Fire crackles and hisses. Eruptions boom. The earth itself seems to shout when it moves. Sound and violence are so intertwined in human experience that to separate them seems unnatural. Yet on Io, that is exactly what happens. The most violent, geological activity in the solar system unfolds in absolute, perfect silence. The reason is simple but profound. Sound requires a medium. It travels as waves of pressure through air, water, or solid materials. Without a medium, there can be no sound, no matter how violent the source. And Io's atmosphere, such as it is vanishingly thin, roughly 1/1000th the pressure of Earth's air at sea level. It is barely more than a vacuum. When a volcano erupts on Io, ejecting molten rock hundreds of kilometers into space, creating plumes that spread across thousands of square kilometers, no sound accompanies it. The explosion that would deafen anyone nearby on Earth occurs in utter quiet on Io. The gases roar outward, the particles stream upward. The energy is immense, but it all happens in silence. This creates a strange contradiction at the heart of Io's nature. It is violence without noise, fury without thunder, chaos unfolding in stillness. Imagine, for a moment, standing on Io's the surface. The ground beneath your feet is coated in sulfur, frost, yellow, and brittle. In the distance, you see a plume rising from the horizon, a vast column of gas and particles extending upward into the black sky. It arcs outward, spreading like a fountain, material falling back to coat the ground in wide circles. You watch this immense eruption, one that would be heard for hundreds of kilometers on Earth, and hear nothing. Not a whisper, not the faintest sound. Nearby, a lava lake churns. Its surface darkens as crust forms, then cracks open, revealing glowing orange molten rock beneath. The crust overturns, sinking back into the lake as fresh material wells up. This happens continuously, a restless cycle of heating and cooling. On Earth, you would hear the crack of breaking crust, the hiss of escaping gas, perhaps the liquid sound of molten rock moving. On Io, you hear nothing. The lake churns in perfect silence, its violence entirely visual. A landslide tears down the slope of a mountain. Thousands of tons of rock tumbling kilometers downward, crashing against the surface below. On Earth, the noise would be tremendous, audible for great distances. On Io, the rocks fall in silence, raising dust that settles back without a sound. This silence is one of the most alien aspects of Io. It removes the visceral impact of the violence, making it easier to contemplate, easier to find beautiful despite its destructive nature. The eruptions become like a silent film, all motion and light, but no soundtrack. They are theatrical, but not assaulting, dramatic, but not overwhelming. For spacecraft visiting Io, this silence is absolute. Instruments can measure heat, detect particles, observe light, but no microphone could record sound, because there is nothing to record. The violence exists purely in the spectrum of electromagnetic radiation and physical motion. It is silent fury, contained in wavelengths invisible to human ears. Yet paradoxically, this silence makes Io easier to study. On Earth, volcanic eruptions are dangerous not only because of lava and ash, but because of sound pressure waves that can damage organs, shock waves that can knock people down, the overwhelming noise that disorients and frightens. On Io, an observer could, if protected from radiation and cold, watch eruptions from relatively close range without being assaulted by sound. The violence would be visible but not audible. The contradiction extends further. Fire itself, as we know it on Earth, cannot exist on Io. Fire requires oxygen, fuel, and heat. Io has heat in abundance, but its atmosphere contains no oxygen. And the fire we see is not combustion, but the glow of molten rock and the emission of thermal radiation. It is fire in appearance, only heat without flame, glow without burning. Even the word eruption carries auditory associations. We think of Mount Street, Helens, of Krakatoa, of explosions that could be heard across continents. But Io's eruptions are not explosions in the conventional sense. They are releases of pressure, fountains of gas expanding into vacuum, driven by internal heat rather than chemical reactions. They look like eruptions, they have the energy of eruptions, but they make no sound. This silence also means that there are no warning sounds on Io. On Earth, volcanoes often rumble before they erupt, giving some warning to those nearby. Earthquakes make sounds as rocks fracture. Io's violence comes without acoustic precursors. The ground might flex and fracture silently. A plume might begin without announcement. The only warnings would be visual or instrumental heat signatures, changes in elevation, the first appearance of gas. The contradiction between violence and silence creates a strange aesthetic. Io is beautiful in photographs, its colours vivid, its plumes dramatic, its lava lakes glowing. But we process these images in silence, or perhaps with gentle music or narration added later. We never hear Io because there is nothing to hear. The violence is sanitized by the absence of sound, made palatable, even soothing. This is why Io can be contemplated peacefully, despite its fury. We see the eruptions but do not hear them. We understand the violence intellectually but do not experience it viscerally. The silence creates distance, allowing wonder without fear, fascination without dread. Yet the contradiction reminds us of the alienness of Io. A world where fire makes no sound is fundamentally different from Earth. It operates by the same physical laws, but in conditions so different that the outcomes seem impossible. To understand Io is to understand that violence need not be loud, that fury can be silent, that the most extreme geological activity in the solar system can unfold in perfect quiet. This silence is also a reminder of the vacuum of space itself. Most of the universe exists in silence. Stars burn without sound. Galaxies collide without noise. Supernovae explode in perfect quiet. Their immense energy, spreading outward as light and particles, but never as sound, because there is no medium to carry it. Io is not unique in its silence. It is typical of the cosmos. Earth, with its thick atmosphere that carries sound across landscapes, is the exception. To think of Io burning silently in space is to think of the universe as it mostly is vast, violent, and utterly quiet. It is a reminder that our human experience of sound is limited to places with air, that most of existence unfolds in silence, that even the greatest catastrophes make no noise if they occur in vacuum. The contradiction of fire without sound is therefore not just about Io. It is about the nature of space itself, about the differences between our world and the countless others that fill the universe. It is a reminder that assumptions based on Earth do not always apply elsewhere, that violence and noise are not necessarily coupled, that silence can coexist with extremes. As we carry this understanding forward, we hold the image of Io's eruptions in our minds, vast plumes rising into space, lava lakes churning, mountains crumbling, all unfolding in absolute silence. It is strange, contradictory, and somehow peaceful. Violence without sound, fire without noise, a world burning eternally in stillness. When Voyager revealed Io's violent volcanic activity in 1979, it confirmed predictions, but also demanded deeper explanation. Scientists could observe the eruptions, measure the heat flow, catalogue the plumes and lava lakes, but observation alone was not enough. The fundamental question remained: why? What drove this small moon to such extremes? The answer lay in forces invisible to cameras, but undeniable in their effects. The answer was gravity. Gravity is among the most familiar forces in daily life, yet also one of the most profound. It keeps us on Earth's surface, governs the orbits of planets, shapes galaxies. Isaac Newton described it mathematically in the 17th century. Albert Einstein revealed its deeper nature in the 20th, showing that gravity is not a force in the conventional sense, but a curvature of space-time itself. Yet regardless of the theoretical framework, gravity's effects are real and measurable. For Io, gravity is not just a force holding it in orbit, it is a source of energy, a furnace that heats the moon from within, a relentless power that will not allow rest. The process is called tidal heating. Though the name can be misleading, we think of tides as the rise and fall of ocean water on Earth, caused by the moon's gravitational pull. But tides are more general, any deformation of a body caused by the uneven gravitational pull of another object. On Earth, the moon pulls slightly harder on the side of the planet facing it than on the far side. This differential pull creates a tidal bulge, stretching the Earth slightly. Because Earth rotates and the moon orbits, this bulge moves around the planet, causing ocean tides. The solid Earth experiences tides too. The ground itself rises and falls by centimeters twice daily, but we rarely notice. For Io, the situation is far more extreme. Jupiter's gravitational pull is immense, and Io orbits close enough to experience significant differential forces. If Io's orbit were perfectly circular, it would always be at the same distance from Jupiter, and the tidal bulge would be constant. The moon would quickly become tidally locked, as it is, with the same face always toward Jupiter, and the internal stresses would stabilize. Friction would cease, heat generation would stop, and Io would cool. But Io's orbit is not circular. It is slightly elliptical, with an eccentricity of about 0.004. That sounds tiny, less than 0.5%, but it is enough. As Io moves closer to Jupiter in its elliptical path, the tidal forces increase. The moon is squeezed more strongly. As it moves farther away, the forces decrease, and the moon relaxes slightly. This cycle repeats every 1.769 days as Io completes each orbit. Squeeze, release, squeeze, release, over and over. Billions of times, over billions of years. The solid rock of Io's interior cannot flex perfectly. There is friction, resistance, heat generation. The moon is literally being kneaded by Jupiter's gravity, and that kneading produces enough heat to melt rock. The amount of energy involved is staggering. Estimates suggest Io generates more than 100 trillion watts of heat through tidal dissipation, roughly 100 times more than all of Earth's internal heat flow. This is not a minor effect or a subtle heating. It is enough to melt significant portions of Io's interior, creating a layer of partially molten rock beneath the crust, possibly even a global magma ocean. But why is Io's orbit elliptical in the first place? Left to itself, tidal forces would circularize the orbit over time, eliminating the eccentricity and shutting down the heating. The answer lies in Io's relationship with its sibling moons, Europa and Ganymede. The three moons are locked in an orbital resonance, a precise mathematical relationship where their orbital periods are related by simple ratios. For every time Ganymede completes one orbit, Europa completes exactly 2, and Io completes exactly 4. This 4, 2, 1 resonance is stable and has likely existed for billions of years. The resonance means that at regular intervals, the moons align in predictable configurations. These alignments create gravitational tugs that, though small compared to Jupiter's pull, are persistent and systematic. Europa and Ganymede's gravity nudges Io's orbit, preventing it from becoming circular. Every time tidal forces try to make the orbit more circular, the resonance pumps eccentricity back in. It is a gravitational feedback loop. Jupiter's tides try to circularize Io's orbit. The resonance with Europa and Ganymede maintains the eccentricity. The eccentricity enables tidal heating. The heating erupts as volcanism. The system is stable because all the elements balance. Remove any one piece, the resonance, Jupiter's gravity, Io's orbital position, and the system would collapse. Io would cool and quiet. This theory of tidal heating, worked out primarily by Stanton Peele, Patrick Casson, and Ray Reynolds, in a paper published just before Voyager 1 arrived, explained not only why Io should be volcanic, but also predicted the scale of the activity. They calculated the heat flow, estimated the degree of melting, and concluded that Io should be the most volcanically active body in the solar system. Voyager's observations confirmed every prediction. The theory was not just correct in principle, but quantitatively accurate. This was a triumph of physics, a demonstration that understanding fundamental forces, gravity, orbital mechanics, friction, could predict geological activity on a world hundreds of millions of kilometers away, sight unseen. The pull of giants is therefore not metaphorical. It is literal. Jupiter, with its immense mass, physically stretches and compresses Io with every orbit. Europa and Ganymede, though smaller, maintain the orbital configuration that enables the heating. Together, these giants conspire to keep Io in a state of perpetual geological violence. This understanding also revealed why Io is unique among Jupiter's moons. Europa experiences tidal heating too, but less intensely because it orbits farther out and its eccentricity is smaller. The heat is sufficient to maintain an ocean beneath its icy shell, but not to create surface volcanism. Ganymede, farther still, shows evidence of past heating but is largely quiet now. Callisto, outermost of the four, is geologically dead, its surface preserving billions of years of history. Only Io, caught in the inner position of the resonance, experiences heating extreme enough to dominate its geology. It is the victim of circumstance, its position and orbital configuration sealing its fate. The theory also explained Io's lack of water. Despite forming in the same region of the solar system as its siblings, Io is notably dry. The reason appears to be its extreme heating. Any water that once existed on or in Io has been baked away, evaporated by the intense volcanic activity and lost to space. What remains is a world of rock and sulfur, all the volatiles driven off by endless heat. For planetary scientists, tidal heating was not entirely new. The concept had been discussed for Europa and other bodies, but Io demonstrated its power on an unprecedented scale. It showed that tidal forces could rival or exceed radioactive decay as a heat source, that small bodies could remain active for billions of years if the right orbital conditions existed. This has profound implications beyond Jupiter. Moons around Saturn, like Enceladus, show evidence of tidal heating. Exoplanets orbiting close to other stars might experience similar effects. Tidal heating is not a curiosity limited to Io, but a fundamental process that shapes worlds throughout the universe. The pull of giants' gravity as a source of geological energy thus became one of the great insights of planetary science. It showed that activity is not limited to large bodies with abundant internal heat. Even small moons can burn if they are caught in the right gravitational trap, stretched and squeezed by forces they cannot escape. Io is the extreme example, the clearest demonstration, the proof that gravity alone, channeled through orbital resonance and tidal forces, can create a world more geologically active than Earth itself. It is a world shaped by invisible hands, by mathematics and physics, by the pull of giants that will not let it rest. One flyby can reveal a world. 2 flybys can show change. But to truly understand a restless body like Io requires patience, persistence, and return visits spread across decades. The investigation of Io did not end when Voyager's images stunned the world in 1979. It was only beginning. Voyager 1 and Voyager 2 together spent only hours in close proximity to Io, capturing hundreds of images that transformed understanding but left countless questions unanswered. How constant was the volcanic activity? Did eruptions come and go, or were they permanent features? How fast did the surface change? What drove the variations in heat output? Were there cycles, patterns, rhythms beneath the apparent chaos? These questions could not be answered by flybys alone. They required sustained observation, the kind that only a spacecraft orbiting Jupiter could provide. That spacecraft was Galileo, and its 8-year mission from 1995 to 2003 revolutionized understanding of Io just as profoundly as Voyager had revealed it initially. But even before Galileo arrived, astronomers found ways to watch Io from Earth. Advances in infrared telescope technology in the 1,980 seconds and 1,990 seconds allowed detection of Io's volcanic hotspots from ground-based observatories. By measuring infrared light from the moon, scientists could identify regions glowing with volcanic heat, track their brightness over time, and catch especially powerful eruptions even across hundreds of millions of kilometers of space. One of the most dramatic ground-based observations came in 1986, when astronomers detected an enormous outburst from Loki Patera, the giant lava lake that Voyager had imaged. The infrared signature brightened dramatically, indicating that the lake's crust was overturning, exposing fresh, molten rock. This confirmed that Loki was not a one-time feature, but a persistent cycling system that had remained active for at least 7 years since Voyager's visit. These ground observations established that Io's volcanism was not episodic or rare, but truly continuous. Year after year, decade after decade, the eruptions continued. Features visible in Voyager images remained active. New hotspots appeared. The volcanic activity never paused, never entered a quiet period. Io was relentlessly, permanently, volcanic. When Galileo entered orbit around Jupiter in December 1995, it carried instruments specifically designed to study Io in detail. Unlike Voyager's brief encounters, Galileo could return repeatedly, observing Io from multiple angles and distances, tracking changes over months and years rather than hours. The spacecraft made 11 close flybys of Io between October 1999 and February 2002, approaching as close as 300 kilometers above the surface. Each flyby added layers of understanding, revealing new eruptions, documenting surface changes, measuring temperatures and compositions with unprecedented precision. One of Galileo's most significant contributions was documenting how rapidly Io's surface changed. Images of the same regions, taken months or years apart, showed dramatic differences. Bright plume deposits faded or were buried. Dark lava flows appeared where none had existed before. The colors shifted as sulfur deposits sublimated and reformed. Mountains showed evidence of fresh landslides. In one striking example, a region near the volcano Pilon Patera appeared dramatically different in images taken just months apart. Where earlier images showed yellowish sulfur plains, later images revealed a vast dark deposit more than 400 kilometers across. Galileo had caught the aftermath of one of the most powerful eruptions ever observed on Io, an event that deposited dark pyroclastic material over an area larger than the entire state of Arizona. The Pilon eruption was particularly interesting because ground-based infrared observations had detected intense heat from the region during the eruption itself. By combining the Earth-based data showing the eruption in progress with Galileo's before and after images showing the results, scientists pieced together a complete picture of a major volcanic event from beginning to end. Galileo also revealed the extraordinary temperatures of Io's lava. Infrared spectrometers measured surface temperatures exceeding 1,600 degrees Celsius at active volcanic vents far hotter than typical basaltic lava on Earth, which flows at around 1,000 to 1,200 degrees. These temperatures suggested ultramafic lavas, rich in magnesium and iron, similar to the ancient lavas that covered Earth billions of years ago but no longer erupt today. This discovery connected Io to Earth's distant past, suggesting that watching Io's volcanism was like watching a geological time machine, seeing processes that shaped our own planet when it was young and hot. Galileo's repeated observations also revealed patterns in Io's volcanic activity. Some volcanoes appeared persistently active across multiple flybys. Others brightened and dimmed in cycles. Loki Patera showed a regular pattern, brightening approximately every 540 days as its lava lake overturned one of the most predictable geological events in the solar system. Other volcanoes were more erratic. Prometheus, a volcano with a long, dark flow field, appeared active in every Voyager and Galileo observation, earning it the nickname Old Faithful of Io. Its plume had been erupting continuously for at least 2 decades, perhaps much longer. The investigation also revealed Io's interaction with Jupiter's magnetosphere in unprecedented detail. Galileo's magnetometer detected the electrical currents flowing between Io and Jupiter, measuring the Io flux tube, a stream of charged particles connecting the Moon to the planet's upper atmosphere. This flux tube carries millions of amperes of current, making it one of the most powerful electrical circuits in the solar system. The particles escaping from Io's volcanoes feed the Io plasma torus, a vast donut-shaped cloud of ionized gas encircling Jupiter along Io's orbital path. Galileo's instruments mapped this torus in detail, showing how it glowed in ultraviolet light and how its density varied with Io's volcanic activity. When eruptions intensified, more material escaped into space, thickening the torus. When activity subsided slightly, the torus thinned. This connection between surface volcanism and space environment demonstrated that Io was not just a moon, but an active participant in shaping the entire inner Jovian system. Its eruptions had consequences that rippled outward for millions of kilometers. Galileo's investigation also attempted to probe Io's interior through measurements of its gravity field. By tracking tiny changes in the spacecraft's trajectory during close flybys, scientists could infer the distribution of mass within the moon. The data suggested that Io had a large iron core, a rocky mantle, and a relatively thin outer shell consistent with models of a partially molten interior heated by tidal forces. The evidence pointed toward a substantial layer of molten or partially molten rock beneath Io's crust, perhaps extending hundreds of kilometers deep. This magma layer would act as a reservoir, storing heat and feeding eruptions at the surface. The constant tidal flexing would keep this layer churned and mobile, preventing it from solidifying despite billions of years since formation. Between Galileo's close-up investigations and continuous ground-based monitoring, the picture of Io became increasingly detailed. It was not just volcanically active but hyperactive, with eruptions ongoing at dozens of sites simultaneously. It was not just hot but extremely hot, with lavas rivaling Earth's most ancient flows. It was not just changing but changing rapidly, reshaping its surface on timescales of months rather than millennia. The investigation also benefited from improving technology on Earth. The development of adaptive optics in the late 1992s and 2000s allowed ground-based telescopes to compensate for atmospheric blurring, achieving resolution approaching that of space telescopes. Observatories like the Keck telescopes in Hawaii and the Very Large Telescope in Chile began producing images of Io that resolved individual volcanic features, tracking eruptions in near real time. By the early 2000s, a global network of observers watched Io continuously. When a major eruption occurred, it could be detected within hours by infrared telescopes and tracked as it evolved. The moon that had been mysterious for centuries was now under constant surveillance, its every flare-up noted and studied. When Galileo's mission ended in 2003, the spacecraft deliberately crashed into Jupiter to prevent contaminating Europa's potential subsurface ocean. It left behind a wealth of data that scientists continue analyzing decades later. More than 35,000 images of the Jovian system, hundreds of them showing Io in exquisite detail, each one a snapshot of a world in constant motion. The investigation continued with NASA's Juno spacecraft, which entered orbit around Jupiter in 2016. Though Juno's primary mission focused on Jupiter itself, it carried instruments capable of observing Io's volcanism. Juno's orbits took it over Jupiter's poles, providing unique views of Io and allowing continued monitoring of the moon's activity. Juno confirmed that Io remained as active as ever, nearly 4 decades after Voyager's discovery. The volcanoes continued erupting, the lava lakes continued churning, the surface continued changing. Nothing had quieted, nothing had cooled. The violence remained constant. The investigation of Io demonstrates how modern planetary science works not as isolated discoveries, but as ongoing campaigns of observation spanning decades, combining spacecraft data with ground-based telescopes, building understanding layer by layer through patience and persistence. We now know Io better than any world except Earth, Mars, and our own moon. We can map its volcanic features, predict some of its eruptions, measure its heat output, and understand the forces that drive it. Yet, mysteries remain. The exact structure of the interior is still uncertain. The mechanisms that focus eruptions at specific locations are not fully understood. The long-term evolution of the day volcanic system remains a subject of debate. But what the decades of investigation have shown beyond doubt is that Io is not an anomaly or a temporary state. It is a permanent condition, a moon forever locked in volcanic violence by forces it cannot escape. The investigation will continue for as long as we can observe Io, because watching a world that never holds still, that changes faster than any other, teaches us about processes fundamental to planetary science. And with each year of observation, each new image, each measurement of heat or composition, we understand better what it means to be trapped between giants, flexed by gravity, unable to rest. We see Io not just as a moon but as a living laboratory, demonstrating tidal heating at its most extreme, showing us what happens when a world cannot find peace. Science thrives on measurement, temperature, distance, composition, energy. These are the language through which we understand the universe. But some things seem almost too extreme to measure meaningfully. How do you quantify violence? How do you capture in numbers the fury of a world that erupts continuously across its entire surface? For Io, scientists have tried, and the data they have gathered is as staggering as the moon itself. Start with heat. The most fundamental measurement of Io's activity is how much thermal energy it radiates into space. Infrared instruments on spacecraft and ground-based telescopes have measured this carefully over decades. The result? Io releases approximately 2 watts of heat per square meter of surface, averaged globally. That might not sound like much until you calculate the total. With a surface area of about 42 million square kilometers, Io's total heat output is roughly 100 trillion watts, 100 terawatts. To put that in perspective, that's about 100 times greater than Earth's total internal heat flow, and Earth is much larger than Io. Where does this heat go? It erupts. It flows in lava. It warms volcanic vents. It sublimates sulfur frost. Every watt of that 100 trillion is generated by tidal friction, by the constant flexing of Io's interior under Jupiter's gravitational kneading. The energy budget is so large that it dominates Io's geology completely. Everything on the surface, every eruption, every flow, every plume is ultimately powered by tidal heating. The temperatures themselves are extraordinary. At active volcanic vents, surface temperatures exceed 1,600 degrees Celsius. Some measurements suggest temperatures as high as 1,800 degrees. These are not just hot by Earth standards, they exceed the hottest lavas currently erupting anywhere on our planet. Such extreme temperatures indicate ultramafic composition, lavas rich in magnesium that only erupt when rock is extraordinarily hot. On Earth, ultramafic lavas existed billions of years ago but disappeared as the planet cooled. On Io, they remain common, making it a window into processes long extinct on our world. The lava lakes present their own measurement challenges. Loki Patera, the largest, covers approximately 21,500 square kilometers an area, roughly the size of New Jersey. Infrared observations show it cycles through brightness variations on a roughly 540-day period, interpreted as the time it takes for the entire lake surface to overturn. As new crust forms and cools, it becomes denser than the molten rock below, eventually sinking and being replaced by fresh magma. The energy required to maintain Loki alone is staggering. Estimates suggest it releases 10 to 20 terawatts during its bright phases, making it one of the most powerful individual geological features in the solar system. The volcanic plumes provide another set of remarkable measurements. The tallest observed plumes reach heights of 300 to 500 kilometers above Io's surface. To achieve such heights in Io's gravity, about 18% of Earth's, the erupted material must leave the surface at velocities of approximately 1 kilometer per second, faster than pound a rifle bullet. The plumes are composed primarily of sulfur dioxide gas that freezes into tiny crystals as it expands into the vacuum. These particles follow ballistic trajectories, arcing outward from the vent and falling back to create the characteristic umbrella shape. The deposition patterns create bright rings around volcanic centers, some extending hundreds of kilometers from the source. Measurements of plume composition reveal not just sulfur dioxide, but also traces of sulfur, sodium, potassium, and other elements. When plumes are particularly powerful, some material escapes Io's gravity entirely, becoming part of the Io plasma torus, an estimated 1 ton per second of material lost to space, continuously for billions of years. The mountains of Io present measurement challenges of a different sort. The tallest, Bo'o Zole Montes, rises approximately 17.5 kilometers above the surrounding plains, about twice the height of Mount Everest. But unlike Everest, which stands as part of a mountain range with a broad base, many of Io's mountains are isolated blocks, tilted slabs of crust thrust upward by internal stresses. Measurements of mountain slope angles reveal values often exceeding 30 degrees, approaching the angle of repose for loose rock. This suggests the mountains are unstable, prone to collapse, their steep faces maintained only temporarily before erosion, primarily through landslides in Io's case, reduces them. The rate of surface change is perhaps the most dramatic measurement of all. By comparing images taken at different times, scientists have documented the appearance of new lava flows covering hundreds of square kilometers in just months. Bright plume deposits fade within years as they are buried or sublimate. The global resurfacing rate, how quickly the entire surface is renewed, is estimated at about 1 centimeter per year. That may sound slow, but integrated over Io's surface, it means that the top meter of Io's crust is replaced every century. Over geologically short timescales of millions of years, the surface has been completely renewed many times over, erasing all record of ancient craters and preserving only the very recent past. Atmospheric measurements reveal the thinness and variability of Io's envelope of gas. The surface pressure varies from less than 1 nanopascal, 1 billionth of Earth's sea level pressure, at night, to perhaps 1 to 10 nanopascals in daylit regions. This atmosphere is primarily sulfur dioxide, sublimating from frost during the day and condensing back at night. During volcanic eruptions, local atmospheric pressure can increase dramatically as gas is released. Some models suggest pressures might reach a few micropascals near active vents, still a near vacuum by Earth standards, but dense enough to drive winds that spread deposits across the surface. The orbital measurements provide the foundation for understanding Io's violence. Io's orbital period is 1.769 days, about 42.5 hours. Its orbital eccentricity is 0.0041, small but crucial. During each orbit, Io's distance from Jupiter varies by about 6,800 kilometers, enough to change the tidal forces significantly. The resulting flexing raises and lowers Io's surface by up to 100 meters during each orbit. Imagine the ground beneath your feet rising by the height of a 30-story building, then falling by the same amount twice every 2 days, forever. The stresses this creates are immense, and they explain the cracking, fracturing, and tilting visible across Io's surface. The magnetic field measurements from Galileo revealed Io's interaction with Jupiter's magnetosphere. The Io flux tube carries an estimated 3 million amperes of electrical current from the Moon to Jupiter's upper atmosphere. This makes it one of the most powerful natural electrical circuits in the solar system, with consequences for both Io's environment and Jupiter's auroras. The Io plasma torus, fed by volcanic emissions, contains an estimated 1 to 3 tons of material per cubic meter in its densest regions. It extends from about 5 to 7 Jupiter radii. From the planet's center, Jupiter's radius is about 71,000 kilometers, forming a vast donut of ionized gas that glows in ultraviolet light. The torus contains sulfur, oxygen, sodium, and other elements in ionized form, all originally from Io's volcanoes. Measurements of Io's mass and density provide clues to its interior structure. With a mean density of 3,528 kilograms per cubic meter, Io is the densest of Jupiter's large moons, indicating a large iron core and rocky mantle with relatively little ice. Models suggest the iron core may be 900 kilometers in radius, surrounded by a rocky mantle extending to the surface. The thickness of Io's lithosphere, the rigid outer shell, is estimated at 12 to 40 kilometers, below which lies partially molten rock that extends deep into the mantle. This molten layer is the reservoir that feeds volcanic eruptions, kept liquid by continuous tidal heating that prevents it from solidifying. The energy budget measurements reveal the scale of tidal dissipation. The total energy dissipated as heat within Io is approximately 10-14 watts. This energy is generated by the conversion of orbital and rotational energy into heat through friction. Over time, this dissipation should cause Io's orbit to decay, but the orbital resonance with Europa and Ganymede continually pumps energy back into the system, maintaining equilibrium. The data also reveals temporal variations. Some volcanoes brighten and dim in regular cycles, Loki every 540 days, others on different schedules. Other eruptions appear sporadic, flaring unexpectedly and then subsiding. The total heat output from Io varies by 10 to 20% over periods of months to years, suggesting that volcanic activity waxes and wanes even though it never stops completely. Measurements of surface composition via spectroscopy reveal sulfur in multiple forms, elemental sulfur in crystalline and amorphous states, sulfur dioxide as frost and gas, polysulfides with complex chain structures. The colors visible in images correspond to these different sulfur species: bright yellow for elemental sulfur, white for sulfur dioxide frost, oranges and reds for altered sulfur compounds. All of these measurements heat flow, temperatures, plume heights, atmospheric pressure, orbital parameters, electrical currents, compositional data combine to create a quantitative picture of Io. The moon is not just qualitatively extreme, but measurably, demonstrably more violent than any other world we have observed. The data transforms abstract concepts like most volcanic or most active into precise statements. Io releases 100 times more heat than Earth's volcanism. Its plumes reach 500 kilometers high. Its lava temperatures exceed 1,600 degrees Celsius. Its surface is replaced every century. Its electrical connection to Jupiter carries megawatts of power. These are not estimates or guesses, but measurements, observations repeated by multiple instruments over decades, confirmed and refined through careful analysis. They are the language in which we quantify Io's violence, the numbers that let us understand not just that Io is extreme, but exactly how extreme it is. And perhaps most remarkably, the measurements reveal not chaos but patterns. Despite the violence, despite the constant change, Io follows rules. Its volcanism is predictable in aggregate, if not in every detail. Its heat output balances its orbital evolution. Its interaction with Jupiter's magnetosphere follows electromagnetic laws. Even in its fury, Io obeys physics, and through measurement, we can understand those laws and predict their consequences. The data shows us that Io's violence, extreme as it is not random but inevitable, the measured, quantifiable result of gravity, orbit, and friction playing out according to natural law. The immeasurable becomes measured, and in those measurements we find not just numbers but understanding. We know Io's surface better than almost any world except our own. Decades of observation have mapped its volcanoes, tracked its plumes, measured its heat, but beneath that ever-changing surface lies a mystery that no spacecraft has directly observed, and no instrument can fully probe the interior of Io, the hidden engine that drives all the visible violence. What lies beneath the crust? Is there a global magma ocean? How deep does the molten layer extend? What is the structure of the mantle, the core? These questions remain partly unanswered, inferred from indirect measurements and theoretical models, rather than direct observation. The deepest we can see into Io is through gravity measurements. When Galileo flew past Io, tracking data revealed tiny variations in the spacecraft's trajectory caused by Io's gravitational pull. These variations reflected the distribution of mass within the moon denser materials, pulling more strongly than lighter ones. The gravity data suggested a layered structure, a dense iron-nickel core approximately 900 kilometers in radius, surrounded by a rocky silicate mantle extending to the surface about 1,800 kilometers from the center. This structure is similar to Earth's, though on a much smaller scale, indicating that Io differentiated early in its history, with heavy elements sinking to the center and lighter materials rising. But the most interesting layer, the one that drives the volcanism, is harder to characterize. Somewhere between the iron core and the solid crust lies a zone of partial melting, a region where rock is hot enough to be partially molten, existing in a state between solid and liquid. This partially molten zone acts as a reservoir for volcanic activity. When tidal flexing generates heat, it accumulates in this layer, melting more rock. When pressure builds, magma rises toward the surface, eventually erupting. The zone is continually replenished by tidal heating, ensuring that it never fully solidifies. How thick is this molten layer? Models vary. Some suggest a relatively thin shell of partial melting, perhaps 50 to 100 kilometers thick, directly beneath the rigid lithosphere. Others propose much deeper melting, extending hundreds of kilometers down, possibly creating a global magma ocean that dominates the upper mantle. The truth likely lies somewhere in between, with the degree of melting varying with depth. Near the base of the lithosphere, rock may be 10 to 20% molten, hot and soft, but still mostly solid. Deeper, the melt fraction might increase to 50% or more, creating regions where magma can move and accumulate. This structure would explain Io's volcanism. The partially molten layer provides the source material for eruptions. The solid lithosphere above acts as a barrier, containing the pressure until it breaks through at volcanic vents. The iron core below provides additional mass and gravity that influences the dynamics of the mantle. But observing this structure directly is impossible with current technology. We cannot drill into Io. We cannot send seismic waves through it to map internal layers. All we have are models, constrained by surface observations, gravity measurements, and our understanding of physics. One clue comes from Io's response to tidal forcing. If the interior were completely solid, Io would flex less, the rigid structure would resist deformation. If it were entirely molten, it would flex more easily. Observations suggest an intermediate response, consistent with a partially molten interior. Another clue comes from the distribution of volcanic activity. If volcanism were driven by a thin crust over a global magma ocean, we might expect eruptions to be evenly distributed across the surface. Instead, they cluster in certain regions, particularly near the equator and in zones of high tidal stress. This suggests that magma doesn't rise uniformly, but focuses along pathways created by fractures and weaknesses in the crust. The mountains also provide evidence about interior processes. The isolated blocks thrust upward by stress suggest that Io's lithosphere is relatively thick and strong enough to support enormous blocks tilted at steep angles without immediately collapsing. Estimates based on mountain stability suggest a lithosphere 12 to 40 kilometers thick. Below this rigid shell lies the mobile zone, where tidal heating occurs. The flexing caused by orbit eccentricity generates the most stress at depths of 20 to 50 kilometers, where rock is hot enough to deform more easily than the cold surface, but not so molten that it flows freely. This is likely where most heat generation occurs. The deeper mantle remains more mysterious. Does convection occur? Are there plumes of especially hot material rising from the core mantle boundary, as on Earth? Or does the tidal heating dominate so completely that deeper processes are irrelevant? Models suggest that convection may be suppressed in Io's mantle because tidal heating provides so much energy at shallow depths. Unlike Earth, where heat from the core drives convection currents that power plate tectonics, Io's heat is generated near the surface, short-circuiting the usual convection cycle. This would make Io's mantle relatively stagnant below the zone of tidal heating, with heat conducted upward rather than carried by convection. The implications are significant. It means Io's interior dynamics are fundamentally different from Earth's, driven by external gravitational forces rather than internal heat sources. The core itself is also not well understood. Is it entirely solid, or does it have a liquid outer layer like Earth's? The answer depends on temperature and pressure conditions we can only estimate. If the core is liquid, it might generate a weak magnetic field through a dynamo process. Galileo detected no such field, suggesting either a solid core or a liquid one too sluggish to generate significant magnetism. One of the deeper mysteries is how long Io has been this way. Has it been volcanically active since formation, or did the heating and activity develop later? The answer affects our understanding not just of Io, but of planetary evolution in general. Some models suggest Io heated up gradually as tidal dissipation accumulated over billions of years. In this scenario, Io might have been quieter in the distant past, becoming progressively more active as the resonance locked in and heating intensified. Other models suggest that once the resonance was established, Io reached its current state relatively quickly and has maintained it ever since. The age of Io's surface essentially zero in geological terms, with everything constantly renewed, means we have no direct record of its past. We cannot look at ancient terrains preserved from earlier epochs. Everything is new, erased, and rewritten again and again. The interior holds the only clues to Io's history, and those clues are hidden from view. Another mystery involves the sulfur. Why is Io so rich in sulfur and its compounds when the other Galilean moons are not? Did Io form with more sulfur, or has volcanic activity concentrated it at the surface over time? And where exactly does the sulfur come from? The mantle, the crust, or both? Some theories suggest that sulfur might be recycled through Io's interior, erupted at the surface, sublimated into the atmosphere, lost to space, and then partially redeposited, creating a complex cycle. Others suggest that deep sulfur-rich layers in the mantle are being tapped by volcanic activity, bringing primordial sulfur to the surface. The mystery extends to the exact mechanisms of eruption. On Earth, most volcanic eruptions are driven by water vapor, When water dissolved in magma turns to steam, it expands violently, propelling the eruption. On Io, water is absent. Instead, sulfur dioxide likely plays a similar role, explosively vaporizing as pressure decreases during ascent. But the details remain uncertain. How much sulfur dioxide can dissolve in Io's ultramafic magmas? At what depths does it exsolve? How efficiently does it drive eruptions? These questions require understanding conditions, temperature, pressure, composition that exist deep within Io's interior, far beyond our ability to measure directly. The deeper mystery of Io's interior is therefore not just about structure but about processes. We know tidal heating occurs. We know magma is generated. We know eruptions reach the surface. But the pathways between cause and effect, the mechanisms that connect gravitational flexing to lava fountains, remain partly obscure. Future missions could help. A spacecraft equipped with a magnetometer sensitive enough to detect induced magnetic fields could reveal the depth and extent of molten zones. Precise gravity mapping from multiple flybys could constrain interior density variations. Even, seismology might be possible if an instrument could survive on Io's surface long enough to record moonquakes generated by volcanic activity. But for now, Io's interior remains hidden, inferred rather than observed, modelled rather than mapped. It is the unseen engine, the hidden furnace, the molten heart that drives all the visible violence, and in its mystery lies part of Io's fascination. The knowledge that beneath the colourful surface we observe so carefully, there lies an entire world we cannot see, a realm of pressure and heat and flowing rock that will likely remain mysterious for decades to come. The interior nobody has seen is where Io's story truly begins, where gravity becomes heat, where orbital mechanics becomes geology, where invisible forces create visible wonders. It is the deepest mystery of all, and understanding it would unlock not just Io's secrets, but fundamental truths about how gravity, orbit, and composition interact to shape worlds throughout the universe. There are moments in science when a piece of theory, perhaps long discussed but never fully appreciated, suddenly becomes the key that unlocks an entire mystery. When the abstract becomes concrete, when mathematics transforms into reality so dramatic that it can no longer be ignored. For planetary science, one such moment came in 1979 with the recognition that tidal heating, a process that had seemed minor, theoretical, almost academic, could create the most violent geology in the solar system. The concept of tidal heating was not new when Voyager reached Jupiter. Scientists had understood for decades that tidal forces, the differential pull of gravity across an extended body, could generate internal friction and heat. The moon causes tides in Earth's oceans and even raises tidal bulges in the solid rock. And this creates friction that very gradually slows Earth's rotation and causes the moon to slowly spiral outward. But these effects on Earth are subtle, measured in centimeters per year or milliseconds per century. They are interesting to geophysicists, but hardly dramatic. The heat generated is negligible compared to Earth's internal radioactive heat. Tidal forces were understood as a minor player in planetary dynamics, a curiosity rather than a primary driver of geological activity. Then came the prediction just weeks before Voyager 1's arrival at Jupiter that changed everything. Stanton Peele, Patrick Casson, and Ray Reynolds published a paper in the journal Science titled Melting of Io by Tidal Dissipation. The paper was remarkable not just for its conclusion, but for its timing and its audacity. The authors started with the known facts. Io orbits Jupiter in a 4-2-1 resonance with Europa and Ganymede. This resonance maintains an orbital eccentricity of about 0.004, As Io moves closer to and farther from Jupiter during each orbit, tidal forces vary, causing the moon to flex. Then came the calculations. How much energy would this flexing generate? The mathematics involved orbital mechanics, material properties of rock, and energy dissipation through friction. When the numbers came together, the result was startling. Io should be generating enormous amounts of heat, far more than could be explained by radioactive decay alone. The paper concluded with a statement that must have seemed almost outrageous at the time. The dissipation is sufficient to melt a large fraction of the mass. Consequences of a largely molten interior may be evident in pictures of Io's surface returned by Voyager. It was a bold prediction, made public just as Voyager was approaching, with images that would either confirm or refute it about to arrive. The timing was either perfectly calculated or remarkably fortunate. Had the paper been published earlier, it might have languished in relative obscurity. Published later, it would have seemed like post hoc explanation. But published just before the images arrived, it became a dramatic prediction immediately, confirmed by observation. When Voyager's images showed active volcanic plumes, smooth crater-free surfaces, and evidence of constant resurfacing, the validation was complete. Tidal heating was not a minor effect or a theoretical curiosity. It was a dominant force, powerful enough to make a moon smaller than Earth's, more volcanically active than our entire planet. This was the turning point. Before this moment, planetary scientists thought about worlds primarily in terms of their internal heat sources, radioactive decay in the mantle and core, residual heat from formation. Large bodies stayed warm longer. Small bodies cooled quickly and became geologically dead. Size was destiny. Tidal heating shattered that paradigm. It showed that external forces, gravity, orbital mechanics, could be just as important as internal heat sources. A small moon could be more active than a large planet if it was in the right orbital configuration. Position and orbital relationships mattered as much as size. The implications rippled outward through planetary science. If tidal heating could do this to Io, what about other moons? Europa, in the same resonance system, should also experience tidal heating. Could it have an ocean beneath its ice, kept liquid by the same process that kept Io molten? The answer, we now know, is yes. Enceladus, a small moon of Saturn showing puzzling activity, might also be tidally heated. Titan, orbiting Saturn in a resonance, might have its methane cycle sustained by tidal warming. The turning point extended beyond our solar system. Exoplanets discovered orbiting close to their stars would experience tidal forces far stronger than Io's. Some might be tidally locked, one face always toward their star. Others might be in eccentric orbits maintained by companion planets. Could they have Io-like volcanism? Could tidal heating make them habitable, despite their proximity to their stars, or uninhabitable because of too much heating? Understanding tidal heating also changed how scientists thought about planetary evolution. A world's history was not just a story of cooling from an initially molten state. It was also a story of orbital evolution, resonances captured or broken, tidal forces waxing or waning. The dance of orbits became as important as the composition and size of bodies. For Io specifically, the understanding of tidal heating explained everything. The volcanism, the smooth surface, the heat flow, the lack of water, all were consequences of being caught in a gravitational trap. Io was not anomalous or puzzling. It was exactly what physics predicted it should be given its orbital situation. The mathematics behind tidal heating, while complex in detail, rests on straightforward principles. When an object is flexed, its internal friction converts mechanical energy into heat. The amount of heat depends on how much flexing occurs, how fast, and the material properties, how easily the material deforms, and how much it resists that deformation. For Io, the flexing is substantial. The surface rises and falls by 100 meters every orbit. The frequency is high every 42 hours, and the material, partially molten rock, has properties that maximize energy dissipation. All factors conspire to create maximum heating. The energy source is Io's orbit itself. Each time Io flexes and generates heat, it dissipates orbital energy. Over time, this should cause the orbit to decay, spiraling Io slowly inward toward Jupiter. But the resonance with Europa and Ganymede continually adds energy back, maintaining the eccentricity. The system is in a kind of steady state. Energy flows from the orbital motion into tidal heating, and the resonance pumps it back in. This energy flow can be quantified. The total power dissipated as heat, roughly 100 terawatts, equals the rate at which orbital energy is being consumed. Without the resonance replenishing this energy, Io would gradually spiral into Jupiter over tens of millions of years. With the resonance, the system can continue indefinitely. The turning point in understanding tidal heating was therefore not just about Io. It was about recognizing a fundamental process that shapes worlds across the universe. It showed that gravity is not just a force that holds things in orbit, but a source of energy that can power geological activity for billions of years. It also demonstrated the power of theoretical prediction in science. Peale and his colleagues did not observe the volcanism and then explain it. They predicted it based on first principles, from mathematics and physics, and then observation confirmed their prediction within weeks. This is science at its most powerful, using theory to predict unobserved phenomena, then testing those predictions through observation. The acceptance of tidal heating as a major geological force was swift. Within months of Voyager's encounter, the planetary science community had embraced the concept. Papers exploring its implications proliferated. Textbooks were revised. Graduate students began dissertations on tidal processes. It became not just an explanation for Io, but a framework for thinking about many worlds. The turning point also showed how interconnected celestial mechanics and geology are. For much of the history of planetary science, these were separate subdisciplines. Orbital dynamics, studied by one group, surface geology by another. Io showed they must be integrated. You cannot understand the geology without understanding the orbit, and the orbit determines the geology. This integration continues today. When studying any moon or planet, scientists now routinely consider tidal effects. Is the body in a resonance? Does it have an eccentric orbit? Could tidal heating contribute to its activity? These questions are standard parts of planetary analysis, and they all trace back to the turning point when Io revealed the power of tidal forces. For the broader public, the concept of tidal heating added a satisfying explanation to Io's strangeness. It was not magic or mystery, it was physics, understandable and quantifiable. Jupiter's gravity, acting through the mathematics of orbital resonance, heated Io from within. Cause and effect were clear, even if the scale was mind-boggling. The turning point also humbled scientists in a good way. It reminded them that nature is often more extreme than we expect, that theoretical possibilities can become dramatic realities, that the universe does not limit itself to the modest examples we see on Earth. Io exists, and therefore we must expand our sense of what is possible. As we carry this understanding forward, we recognize that the turning point was not just about discovering a process, but about transforming perspective. Tidal heating changed how we see not just Io, but the entire solar system and beyond. It showed us that moons matter, that orbital position, determines fate, that gravity itself is a furnace. And it proved that sometimes the most important discoveries are not the observations themselves, but the frameworks that allow us to understand what we observe. The images of Io's volcanoes were stunning, but the understanding of why they exist, that was the true turning point. In the hierarchy of the solar system, planets dominate. They are the massive bodies around which smaller moons orbit, the gravitational anchors that define their local systems. Moons are usually thought of as passive, affected by their planets, but not affecting them in return. They reflect their planet's light, but contribute little else. Io shatters this assumption. It is not a passive satellite, but an active participant in shaping Jupiter's environment. A moon barely 1/4 the diameter of its planet manages to influence phenomena across millions of kilometers of space, creating lights in Jupiter's atmosphere, feeding a vast plasma structure, and maintaining one of the most intense radiation environments in the solar system. The relationship between Io and Jupiter is not one-directional. Yes, Jupiter's gravity torments Io, causing its volcanic violence, but Io strikes back, painting auroras in Jupiter's sky, filling its magnetosphere with plasma and creating electrical currents that connect moon to planet in a circuit of immense power. Start with the most visible consequence, Jupiter's auroras. At the planet's north and south poles, great ovals of light glow constantly in ultraviolet wavelengths, invisible to human eyes but brilliant in spacecraft images. These auroras dwarf Earth's northern and southern lights, spanning areas larger than our entire planet, powered by energies that make Earth's auroras seem faint by comparison. Multiple processes contribute to Jupiter's auroras: solar-wind interactions, the planet's own rotation dragging plasma through its magnetic field. But one of the most dramatic contributions comes from Io. As the moon orbits through Jupiter's powerful magnetic field, it creates an electrical connection, a pathway along magnetic field lines that carries current directly from the moon to the planet's upper atmosphere. This pathway, called the Io flux tube, carries approximately 3 million amperes of electrical current. To put that in perspective, a typical lightning bolt carries about 30,000 amperes. Io's flux tube carries the equivalent of 100 lightning bolts simultaneously, continuously, without pause. Where this current impacts Jupiter's atmosphere, it creates a bright spot in the auroral oval, the Io footprint. This footprint moves across Jupiter's polar regions as Io orbits, tracing out a path that reveals the magnetic connection. Downstream of the main footprint, additional spots appear tail auroras caused by disturbances propagating along field lines. These Io-driven auroras can outshine the rest of Jupiter's auroral oval, making them among the brightest atmospheric features on the planet. They pulse and flicker as Io moves through regions of varying magnetic field strength, and as its volcanic activity varies. When Io's eruptions intensify, more material escapes into space, the plasma density increases, and the auroras brighten in response. The footprint auroras are not just lights but windows into the electromagnetic connection between moon and planet. By observing how they vary, scientists can infer conditions in Io's atmosphere, the strength of volcanic outgassing, and the structure of Jupiter's magnetic field. They are diagnostics, revealing invisible processes through their visible effects. Beyond the auroras lies another consequence of Io's activity, the Io plasma torus. This is a vast, donut-shaped cloud of ionized gas that encircles Jupiter along Io's orbital path. It extends from about 5 to 7 Jupiter radii, approximately 350,000 to 500,000 kilometers from the planet's center, with Io embedded within it. The torus glows in ultraviolet light, particularly in emissions from sulfur and oxygen ions. It is not uniform but varies in density and temperature, with warmer regions near Io's orbit and cooler regions farther out. The total mass of the torus is estimated at roughly 10,000 tons, a substantial cloud by any measure. Where does this plasma come from? Entirely from Io. Every second, approximately 1 ton of material escapes from Io's volcanoes and atmosphere. Some escapes directly during eruptions. Some sublimates from surface frost and is then stripped away by impacts from charged particles. This material is quickly ionized by solar radiation and by collisions with other particles in Jupiter's magnetosphere. Once ionized, the plasma cannot escape. It is trapped by Jupiter's magnetic field, forced to orbit with the planet. Jupiter's rapid rotation, a full day in less than 10 hours, sweeps the magnetic field around, dragging plasma with it. This creates a corrotating magnetosphere, where plasma orbits at the same rate as Jupiter rotates. The plasma torus is therefore a consequence of Io's volcanism, a structure millions of kilometers across, created and maintained by eruptions on a single moon. Without Io, the torus would not exist. Jupiter's inner magnetosphere would be far emptier, far quieter. The torus also affects Io in return. The plasma sweeps past Io at high speeds, about 75 kilometers per second relative to the Moon, because Io orbits more slowly than Jupiter rotates. This bombardment strips away more of Io's atmosphere, creating a feedback loop. Volcanic eruptions create atmosphere. Plasma bombardment removes atmosphere. The cycle continues. The interaction also generates intense radiation. Io orbits through one of the most intense radiation belts in the solar system, created by energetic particles trapped in Jupiter's magnetic field and accelerated to high speeds. Any spacecraft visiting Io must be heavily shielded. Any life form would be quickly sterilized by the radiation dose. This radiation environment is partly Io's own doing. The plasma torus feeds particles into the magnetosphere, some of which are accelerated to high energies, contributing to the radiation belts. Io creates part of the harsh environment it must endure, another feedback loop in the complex system. The electrical currents flowing between Io and Jupiter are another consequence. These currents are driven by Io's motion through Jupiter's magnetic field. As the Moon moves, it acts like a conductor cutting through magnetic field lines, inducing electrical currents through a process similar to how an electrical generator works. The currents flow along magnetic field lines, through Io's ionosphere, and complete the circuit in Jupiter's ionosphere. The total power dissipated in this circuit is estimated at trillions of watts, comparable to the power of all human civilization. This energy contributes to heating both Io's upper atmosphere and Jupiter's auroral regions. The consequence of this electromagnetic interaction is that Io and Jupiter are electromagnetically coupled. They are not just gravitationally bound, but electrically connected. What happens on Io, a change in volcanic outgassing, a variation in atmospheric density, affects Jupiter's auroras and magnetosphere, and changes in Jupiter's magnetic field caused by solar wind variations or the planet's own dynamics affect conditions at Io. This coupling means Io cannot be understood in isolation. It is part of a system, and that system extends well beyond the Moon itself. To understand Io's environment, you must understand Jupiter's magnetosphere. To understand Jupiter's auroras, you must understand Io's volcanism. They are intertwined. The broader consequence is philosophical as much as physical. Io demonstrates that in planetary systems, hierarchies are not absolute. Yes, Jupiter dominates by mass and gravity. But Io, tiny by comparison, creates phenomena that Jupiter cannot create alone. The Moon punches, far above its weight class, shaping a planet thousands of times more massive. This is a lesson applicable throughout astronomy. Small bodies matter. Moons can influence planets. The tail can wag the dog, at least in certain ways. We cannot assume that large objects always dominate every aspect of their systems. Sometimes small, active bodies create disproportionate effects. For scientists studying exoplanets, Io provides a template. When a hot Jupiter, a gas giant orbiting close to its star, has moons, those moons might interact with the planet's magnetosphere, creating auroras, feeding plasma structures. Some of the signals we detect from exoplanets might come not from the planets themselves, but from their moons. Io shows us to look for such effects. The consequence of Io's existence is therefore not limited to the Jovian system. It shapes how we think about planetary systems in general, about the importance of moons, about the interconnectedness of orbital dynamics, volcanism, magnetospheres, and auroras. It shows that studying one object Io requires understanding many: Jupiter, Europa, Ganymede, the solar wind, the plasma environment. As we contemplate Io's influence, we recognize that this small moon is both victim and agent. Victim of Jupiter's gravity, tortured by tidal forces, unable to rest, but also an agent, shaping its planet, creating structures, painting lights, filling space with plasma. It is trapped but not powerless. It is small but consequential. The auroras glowing at Jupiter's poles, visible in spacecraft images as bright ovals of light, are partly Io's signature. The plasma torus extending millions of kilometers through space is Io's creation. The radiation belts that any spacecraft must brave are partly Io's doing. A moon shapes a planet, and in doing so, reminds us that influence flows in both directions in the dance of gravity and light. When we study distant worlds, we are not just cataloguing curiosities or satisfying abstract curiosity. We are learning lessons that illuminate our own world, our own history, and our search for life beyond Earth. Io, despite being utterly unlike Earth, teaches us about our planet in ways both direct and subtle. It is a cosmic laboratory, demonstrating processes that shaped Earth billions of years ago, and processes that might shape worlds we have yet to discover. The first lesson Io teaches concerns heat and energy. For most of Earth's history, our understanding of planetary heat sources centered on radioactive decay and primordial heat from formation. These are the energies that power Earth's plate tectonics, drive our volcanism, and keep the core molten. We assumed all geologically active worlds depended on similar internal heat sources. Io showed us that external forces, gravity, acting through tidal interactions can be equally important. This lesson reshapes how we think about Earth's moon. Our moon was probably more volcanically active in the distant past when it orbited closer to Earth and experienced stronger tidal heating. The lunar maria, vast plains of ancient lava, may have been partly sustained by tidal energy rather than just internal heat. The lesson extends to Earth itself. Though tidal heating is minor for Earth today, it may have been significant early in Earth's history when the moon orbited much closer. Some of the volcanic activity that shaped the early crust, that released gases to form the atmosphere, that created conditions for life, may have been enhanced by tidal heating. Io provides the extreme example, but the principle applies more widely. The second lesson concerns volcanism itself. Before Io, we thought of volcanism as primarily an Earth-like process driven by plate tectonics, involving water vapor as the explosive agent, producing mostly basaltic lavas at temperatures around 1000 to 1200 degrees Celsius. Io shattered these assumptions. Io's volcanism is driven by global heating without plate tectonics. Its Eruptions use sulfur dioxide rather than water as the explosive gas. Its lavas reach temperatures exceeding 1,600 degrees Celsius, rivaling the ultramafic lavas that covered early Earth but vanished billions of years ago. By studying Io, we see volcanic processes that no longer occur on our planet, giving us a window into Earth's ancient past. This is particularly valuable for understanding the Archean and Hadean eons, Earth's first 2 billion years when the planet was hotter and volcanism more intense. The rock record from these periods is sparse. Most has been destroyed by later geological activity. But Io preserves conditions similar to early Earth, allowing us to observe processes we cannot see in Earth's rocks. The ultramafic lavas erupting on Io are chemically similar to komatiites, rare lavas found in some of Earth's oldest rocks. These lavas flowed at extremely high temperatures, creating rivers of glowing rock that moved quickly across the landscape. They probably played a crucial role in forming early continental crust and may have created environments where life's chemical precursors could form. By observing Io's high-temperature volcanism, scientists gain insights into how these ancient processes worked. What are the flow dynamics of such hot lavas? How do they interact with their surroundings? How efficiently do they transport heat? Io becomes a working model of Earth's early volcanic activity, operating today in ways Earth operated billions of years ago. The third lesson involves resurfacing and preservation. Earth's plate tectonics continually recycles crust, subducting old oceanic plates and creating new ones, erasing much of the geological record. But Earth's continents preserve rocks billions of years old, allowing us to study the past. Io represents the extreme opposite, a world where nothing is preserved, where resurfacing is so rapid that all history is erased within millions of years. This teaches us to appreciate Earth's unusual balance. We have enough geological activity to keep the planet dynamic, to sustain life-supporting cycles, but not so much that all history is lost. Io shows what a world looks like when activity overwhelms preservation. It helps us understand why Earth's relatively modest volcanism is actually ideal for maintaining a habitable planet and preserving a geological record. The fourth lesson concerns habitability. Io is definitively uninhabitable. Too hot, too irradiated, too volatile, completely lacking water. Yet studying it helps us understand the boundaries of habitability. How much volcanic activity is too much? At what point does heating become destructive rather than constructive? Io defines the upper limit, showing us where the balance tips from habitable to hostile. This matters for astrobiology and the search for life beyond Earth. When we discover exoplanets in potentially habitable zones, we must consider not just their distance from their star, but their volcanic activity. A planet, slightly too active, might be like Io, geologically fascinating but biologically sterile. A planet with the right level of activity might be like Earth, volcanically active enough to maintain an atmosphere and cycle nutrients, but stable enough for life to persist. The fifth lesson involves moons and their importance. Before the space age, moons were afterthoughts, small bodies orbiting planets, interesting mainly for their orbital mechanics. The exploration of the outer solar system, and Io in particular, revolutionized this view. Moons can be worlds in their own right, as complex and dynamic as planets, sometimes more so. This realization transformed the search for life in the solar system. Scientists now focus as much on moons, Europa, Enceladus, Titan, as on planets. These moons, some heated tidally like Io, might host subsurface oceans where life could exist. Io itself is not habitable, but it demonstrated that tidal heating can keep worlds active and warm, making it plausible that similar heating keeps water liquid beneath Europa's ice. The concept extends to exomoons, moons orbiting exoplanets. We have not yet detected exomoons definitively, but they almost certainly exist. Some might be heated tidally like Io or Europa. Some might be habitable, warmed by tidal energy from their planet, even if the planet itself orbits far from its star. Io taught us to take moons seriously in the search for life. The sixth lesson is about orbital dynamics and resonances. The 4, 2, 1 resonance among Io, Europa, and Ganymede is not unique resonances, appear throughout the solar system and beyond. They can stabilize orbits or maintain eccentricities, leading to consequences like tidal heating. Understanding resonances is crucial for understanding how planetary systems evolve and which configurations lead to interesting outcomes. For example, the TRAPPIST-1 system, a star with 7 Earth-sized planets, has multiple planets locked in resonances. This suggests that tidal heating might be significant for some of them, potentially affecting their habitability. Io provides the template for understanding what such heating does, allowing us to make informed predictions about these distant worlds. The 7th lesson concerns timescales and change. On Earth, we think of landscapes as relatively permanent. Mountains stand for millions of years, coastlines for thousands. Io shows us a world where change occurs on human timescales. Landscapes shift within months. Eruptions alter regions the size of countries in weeks. Everything is temporary. This perspective helps us appreciate both Earth's relative stability and the fact that stability is not universal. It prepares us for the possibility that some worlds we discover will be chaotic, changing too rapidly for detailed mapping or prediction. It also reminds us that Earth itself was probably more like Io in the distant past, more active, more changeable, less stable. The 8th lesson is philosophical. Io demonstrates that the universe contains extremes beyond our daily experience. Fire without sound, volcanoes erupting continuously for billions of years, a surface renewed every century, temperatures hot enough to glow white in darkness, fountains reaching into space. These are not science fiction but science fact, proven by decades of observation. This expands our sense of possibility. If Io exists, what else might exist? What other extremes await discovery? The universe is not limited to Earth-like conditions, Earth-like processes, Earth-like moderation. It includes worlds of fire and ice, of crushing pressures and near vacuum, of geological violence and frozen stillness. Io teaches us to expect the unexpected. For planetary scientists, Io remains an object of intense interest, not despite its differences from Earth, but because of them. Every difference is a lesson. Every extreme is an opportunity to test theories under conditions impossible to replicate in laboratories. Every observation adds to our understanding of how worlds work in general, not just how Io works specifically. For educators and communicators, Io provides a powerful example of how science works: prediction, followed by observation, theory refined by data, understanding built piece by piece through patient investigation. The story of Io, from Galileo's point of light, to Voyager's pizza, to Galileo spacecraft's detailed maps, to continuing ground-based monitoring, is a story of the scientific method in action. And for all of us, whether scientist or not, Io offers a reminder that the universe is vast, diverse, and endlessly fascinating. That small worlds can hold grand lessons. That violence and beauty can coexist. That gravity can be a furnace. Silence can accompany fury. And a moon no larger than our own can teach us about planets, stars, and the possibilities that fill the cosmos. The impact of studying Io extends far beyond the Jovian system. It touches our understanding of Earth's past, our search for life elsewhere, our comprehension of how planetary systems evolve, and our appreciation for the diversity of worlds that exist. It is a small moon with large lessons, a violent world with peaceful teachings, a distant object that helps us understand our own place in the universe. Behind every discovery, beneath every measurement, within every theory, lie people, scientists, who devoted years or decades to understanding a world they could never visit, observers who spent cold nights at telescopes tracking a distant point of light, engineers who built spacecraft to fly past a moon few had heard of. The story of Io is also a human story, one of curiosity, dedication, and the patience required to wring understanding from sparse data across immense distances. Begin with Galileo Galilei himself, though he could never have imagined what that wandering star near Jupiter truly was. By 1610, Galileo was already in his mid-40s, an established mathematician and natural philosopher at the University of Padua. His telescope observations were revolutionary, not just scientifically but personally risky. The idea that Earth was not the center of the universe contradicted church doctrine, and Galileo knew he was treading dangerous ground. Yet he published his observations anyway, driven by something beyond caution, curiosity, conviction, the scientific imperative to share what had been discovered. His sketches of Jupiter's moons, including Io, were crude but careful, positions marked night after night with meticulous attention. He did not know he was observing a volcanic world. He only knew these points of light moved in ways that challenged everything people believed about the cosmos. 3.5 centuries later, another group of observers would reveal Io's true nature. The Voyager team, hundreds of scientists and engineers working across multiple institutions, built 2 spacecraft designed to revolutionize our understanding of the outer solar system. Linda Morabito, the navigation engineer who first noticed the volcanic plume in Voyager 1's images, was in her 20s, part of a new generation entering planetary science just as the space age opened new worlds. Her discovery was almost accidental. She was checking star positions for navigation purposes when the plume appeared in the background. But accidents favor the prepared mind. Morabito recognized that the feature was attached to Io, understood its significance, and brought it to the attention of the imaging team. Her careful attention to detail, her willingness to look beyond the primary task at hand, led to one of the most important discoveries in planetary science. Bradford Smith led the Voyager imaging team, coordinating the work of dozens of scientists analyzing the flood of images returning from Jupiter. The pressure was immense, data arrived continuously, decisions had to be made quickly about which observations to prioritize, and the world was watching. When the volcanic plumes were confirmed, Smith faced the challenge of communicating the discovery to both scientific colleagues and the public, finding language that conveyed the importance without overselling the strangeness. The pizza moon description emerged from this environment, scientists trying to describe the indescribable, reaching for analogies that would make sense to people who had never seen anything like Io. It was informal, almost joking, but it captured the visual truth and helped the public connect with a discovery that might otherwise have seemed too abstract. Stanton Peele, whose paper predicting Io's volcanism appeared weeks before Voyager's encounter, represents another aspect of the human story, the theorist working not with spacecraft or telescopes, but with equations and physical principles. Peele spent years thinking about orbital dynamics and tidal forces, not because he expected to find anything as dramatic as Io, but because understanding how objects move and interact was the core of his discipline. When he and his colleagues realized that the resonance among Io, Europa, and Ganymede should generate substantial heating, it was the culmination of patient theoretical work, not a sudden insight. The mathematics had been there all along. It required careful assembly and interpretation. That, Their prediction was confirmed so spectacularly, was validating but also humbling, a reminder that nature operates according to principles we can understand if we work carefully enough. Torrance Johnson, a key member of the Galileo mission team, devoted much of his career to returning to Io after Voyager's brief encounter. The Galileo mission, from its conception in the late 1972 through its arrival at Jupiter in 1995 to its end in 2003, spanned more than 2 decades, a significant fraction of a professional lifetime. Johnson and others fought for funding, designed instruments, planned observations, analyzed data, all focused on understanding the Jovian system, and especially its innermost volcanic moon. The patience required is difficult to convey. Years passed between mission approval and launch. More years passed in transit to Jupiter. Then came the slow accumulation of data from repeated flybys, each one planned meticulously, each one offering only hours of close observation before Io receded again into the distance. The reward was understanding, built piece by piece, but the process demanded dedication that lasted longer than many careers. Alfred McEwen, a planetary geologist who studied Io's surface changes, exemplifies the ground-based observers who complemented spacecraft missions. Using infrared telescopes in Hawaii and elsewhere, McEwen and colleagues monitored Io year after year, catching major eruptions, tracking the brightness variations of lava lakes, documenting how the moon changed between spacecraft visits. Their work required not just technical skill, but persistent attention. Io had to be observed regularly, night after night when conditions allowed, building a record that spanned decades. These observations were challenging. Io is small and distant, never more than a few arc-seconds across, even in the best Earth-based views. Distinguishing individual volcanic features required pushing telescope technology to its limits. Adaptive optics systems, which compensate for atmospheric blurring, made this work possible starting in the late 1990 seconds. But operating these systems demanded expertise and patience. The human element extends to the many graduate students and postdoctoral researchers who built careers studying Io. They wrote dissertations analyzing Voyager data, conducted experiments to understand sulfur chemistry, developed models of tidal heating, processed Galileo images, and published papers adding incremental understanding. Most are not famous, their names known mainly to specialists, but collectively they built the edifice of knowledge about Io brick by brick. There were setbacks, frustrations. The Galileo spacecraft's main antenna failed to deploy properly, reducing its data transmission rate dramatically. Observations had to be reprioritized. Some planned studies were abandoned. Engineers found workarounds, compressing data more aggressively, but years of work adapting to the failure were required. The scientists and engineers persevered because the alternative giving up was unthinkable. The international nature of planetary science also appears in Io's story. While NASA missions provided much of the data, scientists from Europe, Asia, and elsewhere contributed observations, theoretical work, and analysis. The Io community became global, connected by shared fascination with a moon none would ever visit but all sought to understand. The human element includes moments of wonder alongside the technical work. Scientists who spent years analyzing data still felt awe seeing new images of eruptions, still marveled at the colors, still found beauty in the chaos. The professionalization of science does not eliminate the emotional response to discovery. It channels it, focuses it, but the fundamental human reaction to encountering something extraordinary remains. There were also debates and disagreements, as in any scientific endeavor. Early interpretations of Io's colors sparked arguments about sulfur versus silicate volcanism. the depth of the molten zone, the role of tidal heating in Europa, the predicted activity of newly discovered moons all generated productive controversy. Science advances through such debates, through competing hypotheses tested against evidence, through gradual convergence on explanations that best fit the data. The observers of Io range from Galileo with his crude telescope to modern scientists using instruments millions of times more sensitive. They include engineers who built spacecraft, theorists who never observed the sky directly but contributed essential understanding, and communicators who translated discoveries for public audiences. Each played a role in transforming Io from mystery to known world. What unites them across centuries is curiosity, the desire to understand what lies beyond Earth, to explain the puzzling, to reveal the hidden. Galileo wondered what those points of light were. Voyager scientists wondered what lay beneath the colors. Galileo mission planners wondered how fast the surface changed. Ground-based observers wonder which volcano will erupt next. The human element reminds us that science is not an impersonal mechanism grinding out facts, but a profoundly human activity, driven by curiosity, sustained by dedication, and successful through collaboration. The story of Io is not just about a volcanic moon, but about the people who studied it, who devoted careers and lifetimes to understanding a world they could only observe from afar, who found in that distant point of light something worth understanding. As we continue through Io's story, we carry with us an appreciation for those observers past, present, and future who point their instruments at the sky and ask, "What is that? How does it work? What can it teach us?" Their work, patient and persistent, transforms dots of light into worlds, mysteries into understanding, the unknown into the known. Scientific understanding does not emerge fully formed. It is built through challenge and revision, through hypotheses proposed and tested, through assumptions questioned and sometimes overturned. The story of understanding Io includes not just the discoveries that proved correct, but the ideas that did not survive scrutiny, the debates that shaped interpretation, and the healthy skepticism that ensures only robust conclusions endure. When Voyager first revealed Io's strange colors and smooth surface in 1979, the volcanic interpretation was not immediately unanimous. Some scientists questioned whether the plumes were truly eruptions, or might be geysers driven by subsurface volatiles perhaps, like those on Triton, discovered by Voyager 2 a decade later, though Triton was not yet known when Io was first observed. The composition debate was particularly intense. What were these colourful deposits? Early interpretations focused heavily on sulfur. The yellows, oranges, and reds matched sulfur in various forms and temperatures. Spectroscopic observations confirmed sulfur dioxide frost. It seemed plausible that Io's volcanism was dominated by sulfur rather than silicate rock, perhaps. Io erupted molten sulfur instead of molten rock. This sulfur volcanism hypothesis was appealing because sulfur melts at relatively low temperatures, about 115 degrees Celsius for pure sulfur. If Io's volcanism was driven by sulfur rather than rock, it might not require as much internal heating. The tidal heating calculations would be less extreme. The model seemed more conservative, more in line with expectations for a moon of Io's size. But careful analysis of Voyager's infrared observations told a different story. Some volcanic features were far too hot for sulfur temperatures, exceeding 1000 degrees Celsius, well above sulfur's boiling point. These temperatures required silicate lavas, molten rock. The debate intensified. Were there two kinds of volcanism on Io? Some sulfur and some silicate? Or was all of it silicate, with sulfur compounds merely coating the surface? The resolution came gradually through accumulating evidence. Galileo spacecraft observations in the 1000 990 seconds, measured temperatures exceeding 1,600 degrees Celsius at active volcanic vents far beyond anything sulfur could produce. The hottest features glowed white, indicating ultramafic silicate lavas similar to ancient Earth flows. While sulfur compounds dominated the colorful deposits and frost, the driving volcanism was clearly silicate-based, just extremely hot. This resolution required overturning the more conservative hypothesis. Io's volcanism was even more extreme than initially thought, powered by temperatures rarely seen on modern Earth, sustained by tidal heating on a scale that initially seemed implausible. The conservative interpretation had to give way to the more extreme but correct one. Another challenge involved the depth of heating. How far into Io did the molten zone extend? Early models suggested a relatively thin, partially molten layer beneath the crust, perhaps 50 to 100 kilometers deep. Others proposed deeper melting, possibly a global magma ocean extending hundreds of kilometers down. The debate mattered because it affected predictions about Io's long-term evolution, its response to tidal forcing, and the sustainability of its volcanic activity. Resolving this required gravity measurements from close spacecraft flybys data that came from Galileo's encounters with Io. The results suggested substantial but not complete melting, consistent with a thick, partially molten zone, rather than a thin one or a completely molten mantle. The debate continues in details, but the extreme models, either very shallow or very deep melting, have been largely ruled out. A third area of opposition involved predictions about Europa. If tidal heating made Io so volcanically active, and Europa was in the same resonance system, shouldn't Europa also be volcanic? Early expectations were that Europa might show activity similar to Io, though perhaps less intense because it orbited farther from Jupiter. Instead, Voyager revealed Europa as an ice world, its surface fractured but frozen, with no obvious volcanism. This seemed to contradict the tidal heating model. If the model worked for Io, why not for Europa? Some skeptics pointed to this discrepancy as evidence that tidal heating might not fully explain Io either. The resolution came through recognizing compositional differences. Io, close to Jupiter during the solar system's formation, was too hot to retain much water ice. It formed from rocky and metallic materials. Europa, slightly farther out, retained substantial ice. Tidal heating affects both moons, but in Io it melts rock, while in Europa it keeps an ocean liquid beneath an ice shell. Same mechanism, different outcomes due to different compositions. This realization actually strengthened the tidal heating hypothesis. It could explain both Io's volcanism and Europa's subsurface ocean using the same physical principles applied to different materials. The apparent challenge became supporting evidence once properly understood. A fourth challenge involved the longevity of Io's activity. Could tidal heating really sustain such extreme volcanism for billions of years? Some calculations suggested that the energy dissipation should cause Io's orbit to decay over time, spiraling the moon toward Jupiter on relatively short timescales, millions to tens of millions of years rather than billions. If true, Io's current state would be temporary, a geologically brief phase in its history. This challenge was serious enough that it prompted intensive reanalysis of orbital dynamics. The resolution involved better understanding of how the resonance with Europa and Ganymede maintains the system. The resonance not only maintains Io's eccentricity, but also stabilizes the orbital configuration against decay. Energy dissipated by tidal heating is replenished by the resonance in a steady state balance. Io can maintain its volcanic activity indefinitely for billions of years as long as the resonance persists. Again, what seemed like a challenge to the tidal heating model became an opportunity to deepen understanding of orbital mechanics and resonance systems. A fifth area of debate concerned the role of mountains. Were Io's mountains volcanic constructs like Earth's shield volcanoes, or were they tectonic features thrust up by crustal stress? Early interpretations sometimes assumed volcanic origins because the moon was so dominated by volcanism, but careful analysis of mountain morphology showed they were tilted blocks, not volcanic cones, tectonic features created by compression rather than eruption. This realization required refining models of Io's crust. The lithosphere had to be strong enough to support enormous tilted blocks without immediately collapsing, yet thin enough to allow volcanic eruptions to break through. The balance between strength and weakness, between compression creating mountains and magma breaking through, added complexity to understanding Io's dynamics. Opposition and challenge in science are not obstacles but mechanisms for refining understanding. Every hypothesis questioned, every assumption tested, every alternative considered makes the surviving explanations stronger. The story of Io includes dead ends and revised models precisely because science works through such processes. The debates were sometimes vigorous, occasionally contentious, but ultimately productive. Scientists who initially favored sulfur volcanism accepted silicate volcanism when evidence demanded it. Those who questioned whether tidal heating could sustain Io's activity for billions of years revised their orbital models when calculations showed it could. Assumptions about Europa's volcanic activity were replaced with better understanding of how composition affects tidal heating outcomes. This process of challenge and revision continues. Current debates involve the exact thickness of Io's lithosphere, the degree of melting in the mantle, the mechanisms that focus volcanism at particular locations, and predictions about features yet to be observed in detail. Future observations will resolve some debates and likely create new ones. The opposition in Io's story reminds us that scientific confidence must be earned through evidence, that initial interpretations are often refined or replaced, that healthy skepticism improves rather than impedes understanding. The volcanic model for Io is now firmly established, not because it was obvious from the start, but because it survived decades of challenge, testing, and refinement. As we move forward in Io's narrative, we recognize that what we know now represents current best understanding rather than final truth. New observations, better instruments, and deeper analysis will continue refining our picture of this volcanic world. The process of challenge and revision is not a flaw in science, but its strength, the mechanism through which we approach ever closer to accurate understanding of how nature works. Before Io, when planetary scientists thought about volcanism, they thought about Earth. Volcanoes were features shaped by plate tectonics, driven by water-rich magmas, producing primarily basaltic lavas that flowed at moderate temperatures and erupted episodically from vents distributed along tectonic boundaries. This was the template volcanism, as understood through the only active example we could study in detail. Io shattered that template. It forced a complete reconceptualization of what volcanism could be, where it could occur, how it could be powered, and what extremes it could reach. In the decades since Voyager, planetary science has experienced an awakening of broader, deeper understanding of volcanic processes that transcends Earth-based assumptions and encompasses a spectrum of possibilities revealed by Io and other worlds. The first aspect of this awakening involved recognizing volcanism as a spectrum rather than a single phenomenon. At one end sits Earth's moderate temperatures, water-driven explosions, tectonic controls, episodic activity. At the other extreme sits Io, ultra-high temperatures, sulfur dioxide-driven plumes, global heating, continuous activity. In between lie countless variations, Venus shows volcanism without plate tectonics, driven by plume-like upwellings in a stagnant lid regime. Mars preserves evidence of ancient volcanic activity from a time when the planet was more active. Enceladus sprays water ice into space from fractures at its south pole, powered by tidal, heating cryovolcanism rather than molten rock, but fundamentally similar in being driven by internal energy escaping to the surface. Triton shows nitrogen geysers erupting through ice. Europa likely has cryovolcanism resurfacing parts of its ice shell. This spectrum exists because volcanism fundamentally is about internal energy finding pathways to escape. The specific manifestation, whether molten rock or melted ice, whether explosive or effusive, whether continuous or rare, depends on composition, internal structure, heat sources, and surface conditions. Io represents one extreme outcome when those factors align in specific ways. The awakening included recognizing that plate tectonics, Earth's primary mechanism for heat loss, is not necessary for vigorous volcanism. Io has no plate tectonics, its lithosphere does not subduct, and there are no spreading centers creating new crust. Yet it is more volcanically active than Earth. This overturned the assumption that plate tectonics and volcanism were necessarily linked. Instead, Io showed that global heating can drive global volcanism through a simpler mechanism. Heat generates magma, magma rises, magma erupts, wherever pressure overcomes crustal strength. The distribution is controlled not by tectonic plates, but by crustal weaknesses, by the locations where stress fractures the lithosphere, by random variations in crustal thickness. It is chaotic but effective, capable of producing even more volcanic activity than Earth's orderly plate tectonic system. The awakening also involved recognizing multiple heat sources for geological activity. Earth is primarily heated by radioactive decay and residual formation heat. Io is primarily heated by tidal dissipation. Enceladus likely combines both with possible additional chemistry. Exoplanets might be heated by stellar irradiation if they orbit close to their stars, potentially creating magma oceans on their day sides. This diversity of heat sources means we cannot assume a world size determines its activity level. Small bodies with strong heat sources can be more active than large bodies with weak sources. Io, barely larger than our moon, massively outperforms Mars in volcanic activity, despite Mars being twice as massive. The key is not size but energy input. Another aspect of the awakening concerned volcanic temperatures. Before Io, the hottest lavas thought to exist anywhere were the basalts on Earth at 1000 to 1200 degrees Celsius. Historical komatiites, ultramafic lavas from Earth's Archean period, might have reached 1400 to 1600 degrees, but these were rare and ancient, not observed directly. Io provided the first opportunity to observe ultra-high temperature volcanism in action. Measurements exceeding 1600 degrees Celsius showed that komatiite-like lavas still erupt somewhere in the solar system, allowing scientists to test theories about how such hot lavas behave. The viscosity, flow, speed, cooling rates, and interaction with surroundings of these ancient Earth lavas could be studied through Io's modern examples. This connection between Io and early Earth became one of the most valuable aspects of studying the Moon. Io is not just alien but archaic, preserving conditions that existed on our planet billions of years ago. By understanding Io, we understand Earth's youth a time machine, not in the sense of travelling backward, but of finding a place where ancient conditions persist today. The awakening also transformed how scientists think about volcanic plumes. On Earth, explosive eruptions send ash and gas into the atmosphere, where wind disperses it. The plumes rise kilometre high, but are contained by atmospheric pressure and gravity. They are dramatic but constrained. Io's plumes reaching hundreds of kilometers into space, spreading material across thousands of square kilometers, showed volcanic eruptions in a vacuum uncontained, following purely ballistic physics, creating perfectly symmetrical patterns, impossible on Earth. This expanded the conceptual range of what volcanic plumes could be, from atmosphere-constrained columns to space-reaching fountains. This has implications for understanding volcanic activity on airless bodies. Mercury, the Moon, asteroids all lack atmospheres and would show Io-like plume behavior if they erupted. While none are currently active, understanding how eruptions work in vacuum helps interpret ancient volcanic features on these bodies. Evidence of past volcanic activity can be better understood through Io's modern examples. The awakening extended to recognizing volcanism's role in shaping entire environments. On Earth, volcanoes affect climate, create fertile soils, build islands, but they are one component of a complex system, including oceans, atmosphere, biology, and tectonics. On Io, volcanism is the dominant process, shaping everything: the surface, the thin atmosphere, the interaction with the magnetosphere, the supply of plasma to the Jovian system. This showed that on some worlds, a single geological process can be so dominant that it defines the world entirely. Io is a volcanic moon in a way. Earth is not a volcanic planet. Understanding such monolithic worlds requires different approaches than understanding complex, multi-process worlds like Earth. Another aspect involved recognizing the importance of secondary compounds. Earth's volcanism is primarily about silicate rock, with water as the key volatile. Io's volcanism is also about silicate rock, but sulfur compounds dominate the volatile component and surface chemistry. This combination creates colors, atmospheric composition, and space-environment interactions unknown on Earth. Understanding how sulfur behaves volcanologically, how it melts, flows, vaporizes, condenses, reacts, colors, surfaces, required developing expertise in a chemistry alien to terrestrial volcanology. Io became a laboratory for sulfur geochemistry, revealing processes that might occur on other sulfur-rich bodies throughout the solar system or in exoplanetary systems with different chemical abundances than our own. The awakening also involved recognizing volcanism's connection to orbital mechanics. Before Io, volcanism was studied as a geological process disconnected from astronomy. Orbital dynamics was a separate field. Io forced integration. You cannot understand the volcanism without understanding the orbit, resonance, and tidal forces. Geology and orbital mechanics merged in studying Io. This integration now extends to exoplanets. When discovering a rocky planet orbiting close to its star, scientists immediately consider tidal effects. Is the orbit eccentric? Are there companion planets creating resonances? Could tidal heating drive volcanism or maintain subsurface oceans? These questions, unthinkable before Io, are now standard parts of exoplanet analysis. The awakening in understanding volcanism through Io is ongoing. Each new observation adds nuance. Each improved model refines prediction. Each comparison with other worlds deepens comprehension. But the fundamental transformation has occurred. Volcanism is no longer understood primarily through Earth, but through a cosmic perspective, where Io represents one extreme example of a universal process that manifests differently across diverse worlds. When we look at volcanic features anywhere on Mars, Venus, Mercury, Enceladus, or speculated on distant exoplanets, we now see them through eyes opened by Io. We ask questions Io taught us to ask. We avoid assumptions Io taught us to question. We embrace possibilities Io taught us to recognize. The awakening that Io provided transforms planetary science from geocentric to truly comparative. From Earth analog thinking to recognizing diversity, from limited templates to open-ended exploration of what nature creates when physics operates in different contexts. Io did not just reveal itself, it revealed volcanism as a universal process, richer, more varied, and more extreme than we had imagined. There comes a moment in understanding when accumulated knowledge crystallizes into profound realization, not just knowing facts, but grasping their full implications. For Io, that moment arrives when we truly comprehend what it means that this moon will never quiet, that its fury is not temporary or cyclical, but eternal, or as close to eternal as anything in the universe can be. Io will still be erupting 1,000,000 years from now. 10 million years. 100 million. As long as Jupiter holds it in gravitational embrace. As long as the resonance with Europa and Ganymede persists. As long as the orbit remains elliptical, Io will continue burning. This is not speculation but mathematical certainty. Barring catastrophic disruption of the entire Jovian system, this revelation carries weight. Most geological activity we observe represents a phase, a stage in evolution. Earth's volcanism, though ongoing, has declined from the planet's youth and will continue declining as internal heat dissipates. Mars was once more volcanically active but quieted as it cooled. Venus might still be active, but we cannot observe eruptions, and its volcanism likely varies in intensity over long cycles. Io is different. Its activity level is not declining. It is in steady state, maintained by external forces rather than drawing down finite internal reserves. The tidal heating today equals what it was 1,000,000,000 years ago and what it will be 1,000,000,000 years hence. The eruptions we observe now are not remnants of past glory or brief flare-ups before quiescence. They are the permanent condition, the eternal state. Consider what this means for Io's surface. Every feature visible today will be buried or erased within a few million years, an eye blink in geological time. The mountains will collapse or be covered. The lava flows will be buried beneath newer flows. The plume deposits will sublimate or be overwritten. Nothing survives except the process. Its self-continual renewal, endless erasure, perpetual transformation. Io has no memory. It cannot preserve its history because it destroys all records as fast as they form. Unlike Earth, where we can read billions of years of history in rocks, Io's oldest surface features are likely only millions of years old, perhaps less in many regions. The moon exists in an eternal present, with no past recorded and no foreseeable change in future. This impermanence is total in a way difficult to grasp from our experience on Earth. We live among mountains millions of years old, beside oceans that have existed for hundreds of millions of years, on continents billions of years old. Even our most temporary features, rivers, forests, coastlines, persist for thousands of years at minimum. We are accustomed to landscapes that endure longer than civilizations. On Io, nothing endures. The landscape visible when Voyager flew past in 1979 is already significantly changed. The landscape that will exist when future spacecraft visit will differ from what Galileo observed. There is no permanence, no stability, no constancy except change itself. Yet this impermanence is itself permanent. The process of erasure and renewal will continue indefinitely. Io will always be restless, always be changing, always be young. It is a moon locked in eternal adolescence, never maturing to geological quietude, never settling into the stability that comes to most worlds with age. The revelation extends to understanding Io's place in cosmic time. The solar system is 4.6 billion years old. Io has likely been volcanically active for most or all of that time, 4.6 billion years of continuous eruptions. The Galilean moons probably formed within a few million years of Jupiter itself, and the resonance that drives Io's heating could have established early, trapping Io in its current state from near the beginning. This means Io has been erupting since before Earth's oldest rocks formed, since before life arose on our planet, since before the moon stabilized in its current orbit. While Earth cooled and life evolved and continents formed, Io burned. While dinosaurs rose and fell, while mammals diversified, while humans evolved, Io continued erupting, unchanged in its violence, and it will continue long after Earth's volcanism ceases. Our planet's internal heat is finite. Radioactive isotopes decay, their heat production declining exponentially. The core slowly cools. Billions of years from now, Earth's volcanism will sputter and cease. Plates will stop moving, and our planet will become geologically dead, still orbiting the sun but internally quiet. Io will still be erupting. As long as Jupiter exists, as long as the moons maintain their resonance, the tidal heating continues. Io's power source is gravitational, fed by orbital energy, and that reservoir is enormous. The decay timescale for the resonance system is measured in tens of billions of years longer than the Sun's remaining 2 lifetime. This means Io might outlast Earth's geological activity by billions of years. The small moon will remain active after the larger planet quiets. Size and mass matter less than energy source. Io has tapped into something more sustainable than internal heat. It has harnessed the orbital energy of the Jupiter system, a resource that will not exhaust on any relevant timescale. The revelation also encompasses understanding what eternal means in cosmic terms. Nothing is truly eternal. The universe itself had a beginning and will have an end. But on human timescales, on geological timescales, even on the timescales of stellar evolution, Io's activity is effectively eternal. It will continue for longer than we can meaningfully comprehend, outlasting mountains and oceans, and perhaps civilizations. This permanence of impermanence creates a philosophical paradox. Io demonstrates that change itself can be the stable state, that flux can be constant, that destruction and creation can balance in perpetual dynamic equilibrium. The moon is simultaneously the most changing and most unchanging body in the solar system, always reshaping itself, yet always remaining volcanically active. For humanity observing from Earth, this revelation affects how we think about geological processes. We are accustomed to thinking of volcanic activity as temporary. An eruption lasts days or years. A volcanic field remains active for millions of years. A tectonic regime operates for tens of millions. Even Hawaii, with its long-lived hotspot, represents only a fraction of Earth's history. Io shows that volcanic activity can be truly persistent, lasting as long as the world exists, never pausing, never entering dormancy. It is not a phase, but a permanent state. This challenges our intuitions about how geology works, expanding our sense of what sustained activity means. The revelation carries emotional weight too. There is something almost tragic about Io's condition trapped in violence. It cannot escape, unable to rest, forever tormented by forces beyond its control. Yet there is also something magnificent about it, the refusal to go quietly, the persistent assertion of energy and change, the eternal youth of a surface constantly renewed. Io will never know the peace that comes to most worlds, the calm of geological death, the quietude of internal cooling, the stillness of stable landscapes, but it also will never fade into irrelevance, never become a mere relic of past glory, never be interesting only for what it once was. It remains perpetually vital, perpetually active, perpetually fascinating. As we contemplate this restless eternity, we see Io not just as a moon but as a demonstration of cosmic endurance. It shows that under the right conditions, activity can be sustained, not just for long periods but indefinitely. It proves that the universe contains not just ancient, quiet worlds preserving their past, but also eternal fires that burn without consuming their purse, fuel continuing as long as gravity and motion persist. The revelation is humbling. Humanity has existed for hundreds of thousands of years, civilization for thousands, modern science for centuries. In all that time, Io has never paused its eruptions. It erupted before we existed and will erupt long after we are gone. Our entire history, from first human thought to last, is less than an instant in Io's endless volcanic story. Yet the revelation is also inspiring. Io reminds us that the universe contains wonders beyond our experience, processes operating on timescales that dwarf our own, demonstrations of natural law playing out with relentless consistency. To understand that Io will still be erupting billions of years hence is to touch something close to eternity, to glimpse the deep time in which planets and stars live their lives. The restless eternity of Io is not a curse but simply its nature, the inevitable consequence of orbital mechanics and gravity operating in a particular configuration. It has no choice but to burn because that is what physics demands of a moon in its situation. And in accepting this, we see Io clearly, not as victim or anomaly, but as a world perfectly expressing the natural laws that govern it, forever caught in gravity's grip, forever unable to rest, forever burning in the silent darkness of space. There is something paradoxical about finding beauty in destruction, peace in violence, wonder in chaos. Yet this is precisely what Io offers. Despite being the most volcanically violent body in the solar system, despite its surface constantly destroyed and remade, despite eruptions that would be catastrophic on Earth occurring continuously, Io is beautiful, strikingly, undeniably, unforgettably beautiful. The colours alone captivate. Yellows bright as sulphur crystals catching sunlight, oranges and reds like autumn leaves or desert sunsets, whites pure as fresh snow, blacks deep as volcanic glass. These are not subtle hues requiring careful party examination to appreciate. They are vivid, saturated, painting the moon in contrasts so strong they seem almost artificial. Yet they are entirely natural, the product of chemistry operating at extremes. Sulfur, in different forms and temperatures, creates the spectrum of yellows to reds. Sulfur dioxide frost produces the brilliant whites. Fresh lava flows add the blacks. The colours are consequences of violent eruptions that heat, melt, vaporize, deposit, transform materials, but the result is aesthetic, a palette more diverse than any other world. From orbit, Io resembles abstract art. The plume deposits form great circles, some overlapping like ripples in a pond. The lava flows create dark streaks across colourful plains. The mountains cast long shadows. The patterns seem designed rather than random, though they are entirely the product of physical processes following mathematical laws. No artist planned this composition, yet it achieves a visual harmony that satisfies aesthetic sensibilities. The plumes themselves, when caught in images, possess delicate beauty. Their umbrella shapes are perfectly symmetrical, following ballistic trajectories determined by gravity and initial velocity. Particles rise and fall in graceful arcs, spreading outward in expanding rings. The motion is balletic despite the violent eruptions, powerful enough to throw material hundreds of kilometers high. yet resulting in patterns of mathematical elegance. The silence adds to the aesthetic. Because there is no sound, because the eruptions unfold in vacuum, they become purely visual experiences. We see fire without hearing its roar. We observe fountains without the rush of escaping gas. This separation of sight from sound creates distance, allowing appreciation without visceral fear. The violence becomes contemplative, something to observe and understand rather than flee. The lava lakes glow with otherworldly light. Dark crusts break to reveal orange or white-hot magma beneath. The lakes breathe in slow cycles, brightening as fresh lava wells up, dimming as crust forms, brightening again. This rhythm, visible across millions of kilometers, creates a kind of visual music, a flickering that speaks to processes operating deep within the moon. Even the mountains, fractured and collapsing, possess stark beauty. Their isolated forms rise dramatically from plains, catching sunlight at angles that emphasize their height and steepness. The lack of atmosphere means every detail remains sharp, no softening haze, no atmospheric perspective, just raw geology rendered in perfect clarity. The mountains are monuments to stress, to forces that bend and break rock. Yet their very existence demonstrates the strength of Io's lithosphere, the temporary victory of solid crust over molten interior. The beauty exists at every scale. Close-up images show intricate details, the texture of lava flows, the patterns of frost deposits, the fractures in mountain slopes. Wide views show the bead painted globe, colourful and strange. The beauty is not hidden or subtle, but obvious and immediate, striking even casual observers. This creates a tension between what Io is and how it appears. It is a world of violence, eruptions constant, surfaces destroyed, heat extreme, radiation intense. Any spacecraft approaching too close risks damage. Any human standing on its surface would face instant death from cold, vacuum, radiation, and possibly lava. It is fundamentally hostile to life, to stability, to anything we value about habitable worlds. Yet it appears not hostile but magnificent. The colours delight, the patterns intrigue, the scale awes. Removed from immediate danger, observing from safe distance or through images, we find Io not terrifying but beautiful. The violence that makes it uninhabitable also makes it visually stunning. This paradox appears throughout nature. Hurricanes photographed from space show elegant spiral structures even as they devastate coastlines. Lightning illuminates storm clouds beautifully while delivering deadly energy. Stars exploding as supernovae create nebulae of breathtaking complexity from catastrophic violence. Nature's most powerful processes often produce spectacular aesthetics alongside their destruction. Io fits this pattern but with unusual purity. It is almost entirely violence. There is no calm region, no safe harbour, no place untouched by geological fury. Yet the whole is beautiful, every region contributing to the aesthetic whole. The beauty emerges from the violence rather than existing despite it. This teaches something important about aesthetics and nature. Beauty is not necessarily linked to gentleness or habitability. Mathematical patterns, vivid colours, dramatic contrasts, elegant forms, these can emerge from any process, destructive or creative, gentle or violent. Our aesthetic appreciation responds to pattern and complexity regardless of the underlying mechanism. Io also demonstrates that strangeness and beauty are compatible. The colours, while beautiful, are alien. Nothing on Earth looks quite like Io's sulphur-painted plains. The plumes, while graceful, are unlike anything in terrestrial experience. The mountains, while dramatic, form through mechanisms different from Earth's ranges. Yet this strangeness, enhances rather than diminishes aesthetic appeal. The unfamiliar becomes fascinating precisely because it is unfamiliar. The reflection on beauty and violence also connects to human fascination with extremes. We are drawn to records the tallest, fastest, hottest, most extreme. Io holds many such records. Most volcanically active, highest lava temperatures, tallest plumes. These extremes fascinate not just intellectually but emotionally. Knowing we are observing the most violent geological activity anywhere captures imagination in ways moderate examples might not. Yet the beauty is not just in the extremes, but in the details. The way sulfur frost sublates and reforms creates delicate patterns. The way different lava flows overlap creates stratigraphy visible from orbit. The way plume deposits create rings within rings shows the persistence of volcanic features even as they evolve. These subtleties reward close study, offering layers of aesthetic appreciation beyond the initial visual impact. Photography plays a role in how we perceive Io's beauty. The images returned by Voyager and Galileo, processed and enhanced to bring out details and colours, present Io at its most striking. This is not deception, the colours and features are real, but presentation optimized for human visual systems. The images are simultaneously scientific data and aesthetic objects. This dual nature of planetary images, both data and art, applies especially well to Io. Scientists analyze the images for information about volcanic processes, surface composition, and geological change. But anyone can appreciate them aesthetically, responding to colours and patterns without needing technical knowledge. The images work on multiple levels simultaneously. The beauty and violence that Io exemplifies also offers perspective on human experiences of destruction and renewal. Forest fires destroy but enable new growth. Storms devastate but sculpt landscapes. Even in human life, difficult experiences can lead to growth. Loss can precede renewal. Io's constant destruction and creation cycle, operating on geological rather than human timescales, perhaps resonates with patterns we recognize in our own lives. This is not to romanticize Io's violence or to claim that destruction is inherently good, but it suggests that violence and beauty, destruction and creation are not opposites but often intertwined. Io exists in permanent destruction yet remains young and vital. Its violence is its vitality. The same processes that erase also renew. As we reflect on beauty and violence, we recognize that Io offers a particular kind of aesthetic experience, one that combines grandeur with strangeness, pattern with chaos, familiarity with alienness. It is beautiful not despite its violence, but through it, because of it. The eruptions create the colours. The lava flows create the patterns. The constant change maintains the youth. The beauty and the violence are inseparable, two aspects of the same underlying reality. And perhaps this is the deepest reflection, that beauty exists not as a separate quality added to objects, but as a property emerging from structure, pattern, contrast, and complexity. Io has these in abundance. Its violence creates structure, its processes create patterns, its composition creates contrast, its dynamics create complexity. The result is beautiful because these fundamental elements of aesthetic experience are present, regardless of whether the underlying processes are gentle or violent, nurturing or destructive. To see beauty in Io's violence is not to ignore its hostility, but to recognize that reality contains both. The universe creates wonders through processes that would destroy us. We can appreciate those wonders from safe distance, finding in them both scientific insight and aesthetic pleasure, both intellectual understanding and emotional response. Io teaches us to see beauty broadly, to recognize it in unexpected places, to appreciate the aesthetic dimensions of violence as well as gentleness. We have traveled far in this journey, from Galileo's first observation of a wandering star, to Voyager's revelation of volcanic plumes, to Galileo spacecraft's detailed monitoring, to our current understanding of a world locked in eternal restlessness. We have explored the forces that shape Io, the consequences that ripple through the Jovian system, the lessons it teaches about planets and moons throughout the universe. And now, as this exploration draws toward conclusion, we return to the image that has guided us throughout, a fire that never sleeps. That fire burns tonight as you read or listen to these words. Somewhere on Io's surface, lava is flowing. A plume is rising into space. A lake is overturning its crust. Mountains are fracturing under stress. The surface is being repainted, erased, renewed. This has been happening every moment of every day for billions of years, and it will continue for billions more. The fire that never sleeps is both literal and metaphorical. Literally, Io's lava flows and volcanic vents glow with heat that never fully cools, sustained by energy that never exhausts as long as the orbital configuration persists. The moon is a furnace kept stoked by gravity, its fires fed by the constant kneading of tidal forces. Metaphorically, Io represents something deeper, the persistence of energy and change in a universe often characterized by cooling and quiet. Most worlds age into stillness. Internal heat dissipates. Atmospheres escape. Surfaces freeze. But not Io. It remains vital, active, alive in the geological sense. It refuses the sleep that comes to most worlds, trapped in wakefulness by forces beyond its control. This persistence makes Io unique not just in fact but in meaning. It is a counterexample to entropy's apparent victory, a demonstration that under the right conditions, systems can maintain high-energy states indefinitely. The universe tends toward disorder and cold, but within it exist pockets of sustained order and heat. Stars burn for billions of years, galaxies rotate, and moons like Io erupt without pause. The fire that never sleeps also represents curiosity, humanity's endless questioning, our refusal to accept mystery without investigation, our drive to understand. Galileo glimpsed something strange and looked closer. Voyager scientists saw colors and eruptions and sought to explain. Generations of researchers have devoted careers to understanding this one small world, and future generations will continue. This intellectual fire, like Io's volcanic fire, does not sleep. Each answer prompts new questions. Each observation reveals new complexity. Each model requires refinement. The investigation of Io is not finished, and may never be finished as long as humans can observe it and wonder about it. As we close this exploration, we might ask what Io ultimately means. Is it just an exotic moon, interesting but irrelevant to human life, or does it offer something more? The answer lies in perspective. Io reminds us that the universe is vaster, stranger, and more diverse than our daily experience suggests. It shows that worlds can be fundamentally different from Earth, yet still governed by comprehensible physical laws. It demonstrates that extremes exist in nature that dwarf anything in human experience. These reminders matter. They expand our sense of possibility. They humble us before natural grandeur. They suggest that if Io exists a moon more volcanic than Earth, despite being 1/4 the size, then what else might exist? What other extremes await? Discovery around other stars? What processes we haven't imagined might be operating on worlds we haven't yet observed? Io also reminds us of interconnection. The moon's fate is determined by Jupiter's gravity, and the orbital dance with Europa and Ganymede. Change any element and Io would be different, perhaps quiet, cratered, frozen. The violence exists because of context, because of relationships, because of where and how Io fits into its system. This is true universally. Objects are shaped by their contexts, by their relationships to neighbours and environment. For planetary science, Io represents a triumph of the scientific method. Theoretical prediction: tidal heating should make Io volcanic, followed by observational confirmation. Voyager sees eruptions, followed by decades of detailed study, refining understanding. This is science at its science best. The process demonstrates how human curiosity, combined with mathematics and observation, can unlock secrets across hundreds of millions of kilometers of space. For the rest of us, scientists or not, Io offers something more intangible but equally valuable: a sense of wonder. In an age where much feels explained and mapped, where Earth seems small and thoroughly explored, Io reminds us that wonders still exist. We can point to a spot in the night sky and know that there, invisible to naked eyes but real nonetheless, a moon is erupting continuously, painting itself in colours Earth never wears, burning in silence. That knowledge changes nothing practical in our lives. Io does not affect weather or economics or politics, but it expands the landscape of the mind. It adds richness to our understanding of the cosmos. It gives us something to marvel at, to contemplate, to find beautiful despite its violence and hostile nature. As we return from this journey through Io's story, we carry images with us. The orange and yellow painted globe hanging in space, the vast umbrellas of volcanic plumes arcing hundreds of kilometers high, the glowing lakes of lava churning in slow cycles, the jagged mountains rising from sulfur plains, Jupiter looming enormous in Io's sky, the source of torment and the anchor of existence. We carry understanding too, of tidal heating as energy source, of resonances maintaining orbital eccentricity, of volcanism operating without plate tectonics, of surfaces renewed constantly, of silence accompanying violence, of beauty emerging from extremes. And we carry questions still about the exact structure of Io's interior, about the mechanisms focusing eruptions at specific locations, about the long-term evolution of the Jovian system, about similar worlds that might exist around distant stars. The fire that never sleeps will still be burning when these questions find answers. It will burn when those answers prompt new questions. It will burn regardless of whether anyone observes it, indifferent to human curiosity, but fascinating precisely because we can observe and understand it. In closing, return to the beginning of this journey. Remember the initial image: a small moon caught in the gravitational grip of a giant planet, unable to rest, unable to cool, forever erupting. That image remains accurate, but now carries deeper meaning. We understand why the moon cannot rest orbital resonance and tidal heating lock it in violence. We know what that violence produces: lava flows and plumes and painted surfaces. We grasp the consequences: plasma, tori and auroras, and lessons for planetary science. The fire that never sleeps is not just a description, but an invitation to observe, to wonder, to understand, to appreciate. It invites us to look beyond our world, to embrace the strange and extreme, to find beauty and meaning in a moon that burns eternally in the cold darkness of space. So let Io's fire accompany you into rest tonight. Let its silent eruptions, its colourful plains, its restless energy become a meditation on persistence, on change, on the wonders that fill the universe. Let the knowledge that somewhere, right now, a world is burning without sound, bring not disturbance but strange comfort, a reminder that energy and change continue, that the universe is vast and active, that wonders exist beyond our immediate sight. The fire that never sleeps burns on, has always burned, will always burn, and we, briefly conscious observers on a distant planet, have the privilege of knowing it, understanding it, and finding in it both knowledge and wonder, both science and beauty, both fact and inspiration. Io, the most violent moon in our solar system, the world that cannot rest, the fire that never sleeps, we have told its story as best we can, and in telling it, we have touched something eternal, something beyond human timescales, something that will outlast us and continue long after we are gone. That is perhaps the deepest lesson of all, that the universe contains processes and wonders that transcend our brief existence, operating on scales that dwarf our own but remain incomprehensible through patient study and honest curiosity. Good night, and as you close your eyes, remember that far beyond Earth, beyond Mars, beyond the asteroid belt, in the cold realm where Jupiter dominates, a small moon burns silently in darkness, erupting, changing, unable to rest, the fire that never sleeps, forever.